Time stands as the ultimate framework of our universe, the invisible tapestry upon which all physical reality unfolds. It measures the progression of existence, allowing us to sequence events and understand cause and effect. Unlike objects we can touch or see, time exists as a continuous flow, structuring our perception of the cosmos and defining how we experience reality itself. At its essence, time provides organization to the universe. A second is defined by the vibrations of cesium atoms in atomic clocks, a day by Earth's rotation, and a year by our planet's journey around the sun. These natural cycles give time tangible presence, enabling us to measure and organize the world around us. Without time, events would have no sequence, motion would carry no meaning, and change would be impossible to comprehend. Time does more than simply measure. It exists as a fundamental dimension of reality. It governs how processes unfold, from the orbital dance of planets to the rhythms of biological existence. Plants grow, tides shift, and seasons change in accordance with time's steady progression. Even our consciousness experiences reality through time's linear framework, creating the narrative structure of our lives. The measurement of time has evolved throughout human history. Ancient civilizations tracked celestial movements, creating calendars to predict seasonal changes and organize society. Water clocks and sundials gave way to mechanical timepieces, eventually leading to today's atomic clocks, accurate to within billionths of a second. Yet, despite our increasingly precise measurements, time itself remains mysterious, an integral component of space-time that bends near massive objects as predicted by Einstein's relativity. Time's directional nature creates what physicists call the arrow of time, pointing from past to future. This asymmetry manifests in entropy, the tendency of organized systems to become more disordered. A dropped egg shatters, but the fragments never spontaneously reassemble. This irreversibility demonstrates time's fundamental directionality, distinguishing it from spatial dimensions we can traverse in any direction. In quantum physics, time takes on even stranger properties. Particles can become entangled, showing coordinated behaviors regardless of distance, seemingly instantaneous across space-time. At the smallest scales, time's continuous flow breaks down into discrete units. The Planck time, approximately 10 to the negative 43rd seconds, representing the smallest, meaningful measurement of time possible. Time dilation, the slowing of time under certain conditions, challenges our intuitive understanding. Clocks on GPS satellites run slightly faster than identical clocks on Earth due to weaker gravitational fields and relative motion, requiring correction to maintain accuracy. This confirms Einstein's prediction that time flows differently depending on relative motion and gravitational strength, proving time isn't absolute but relative to the observer. The perception of time varies throughout nature. Some processes occur in nanoseconds, like chemical reactions, while others span billions of years, like stellar evolution. Biological organisms experience time according to their metabolic rates. A hummingbird experiences the world in slow motion compared to our perception, while a tortoise's perception likely compresses longer time frames than ours. Time binds together all other physical concepts. Forces require time to act. Energy transfers over time, and motion itself is change in position over time. Even in seemingly timeless equations like E equals mc squared, time hides within the speed of light, constant. Without time, Physics would be static, a collection of potential states without transition or causality. As we explore further physics concepts, remember that time forms the foundation upon which all other physical phenomena occur. It is both the simplest concept to grasp, we experience it constantly, and among the most profound, challenging philosophers and physicists alike, with its mysterious nature. Time isn't merely something we measure with clocks. It is the flowing essence of reality itself, the dimension that gives meaning to existence and structure to the universe. Position represents the fundamental reference point for all motion in the physical world. Every object exists somewhere in space, and describing its position is the first step in understanding how objects move and interact. Unlike time's constant flow, position is purely spatial, defining the exact location of an object at a specific moment. In physics, position requires a coordinate system, a framework that assigns numbers to locations in space. The simplest form is a one-dimensional number line, where moving forward increases position values and moving backward decreases them. Real-world movement typically occurs in higher dimensions. 2 dimensions for movement across a surface, using coordinates like latitude and longitude on Earth's surface, and 3 dimensions for objects moving freely through space, with X, Y, and Z coordinates pinpointing exact locations. Position's relativity represents one of its most crucial aspects. No absolute reference point exists in the universe. Position must always be measured relative to something else. When you describe an object as 3 meters to the right, you implicitly define a reference point and direction. This relative nature of position leads to the concept of frames of reference, different perspectives from which movement can be observed and measured. The importance of reference frames becomes apparent in everyday scenarios. A passenger on a train might perceive themselves as stationary while trees and buildings rush past, but an observer on the ground sees the train and its passengers moving rapidly. Both perspectives are equally valid despite their contradictory appearances. This principle extends to cosmic scales. Earth rotates at approximately 1,000 miles per hour at the equator and orbits the Sun at about 67,000 miles per hour, yet we perceive ourselves as stationary because our reference frame moves with us. Position plays a central role in navigation systems that have transformed modern life. GPS satellites constantly transmit their positions, allowing receivers to calculate their own positions through triangulation. Autonomous vehicles determine their positions relative to roads and obstacles, enabling self-driving capabilities. Even your smartphone contains accelerometers and gyroscopes that track position changes to orient the screen or count your steps. In quantum mechanics, position takes on probabilistic properties that challenge classical intuition. Heisenberg's uncertainty principle demonstrates that we cannot simultaneously know a particle's exact position and momentum with perfect precision. The more accurately we measure position, the less certain momentum becomes, and vice versa. At quantum scales, particles exist as probability distributions rather than definite points, with their positions described by wave functions that indicate the likelihood of finding the particle at different locations when measured. The mathematics of position becomes more complex when dealing with accelerating reference frames or strong gravitational fields. Einstein's general relativity reveals that massive objects curve the fabric of space-time, altering how we define position in their vicinity. Near black holes, this curvature becomes so extreme that our usual notions of position break down entirely, requiring more sophisticated mathematical frameworks. Position's relationship with time creates the concept of displacement, the change in position over a given time interval. While position tells us where something is, displacement reveals how its position has changed. This seemingly simple concept becomes the foundation for understanding velocity, acceleration, and ultimately forces that shape the physical world. Astronomers use position measurements to remarkable precision, tracking the locations of distant celestial objects and spacecraft venturing through our solar system. The position of stars shifts slightly as Earth orbits the Sun, creating stellar parallax that allows astronomers to calculate their distances. NASA engineers calculate positions with such accuracy that spacecraft can thread the needle between Saturn's rings or rendezvous with asteroids after journeys of hundreds of millions of miles. Geologists rely on position data to track the imperceptibly slow movement of tectonic plates, typically just centimeters per year, using highly sensitive GPS measurements. This allows them to monitor fault lines, predict volcanic activity, and better understand the dynamic processes reshaping Earth's surface over geological timescales. Even in quantum teleportation, a phenomenon where quantum information appears to instantly transfer between entangled particles, position plays a crucial role. While the process doesn't actually move objects as depicted in science fiction, it transfers the quantum state from one position to another, highlighting the deep connection between information and physical location in quantum physics. Position sets the stage for understanding the physical world by giving us the fundamental concept of where. As we explore increasingly complex physical phenomena, remember that knowing an object's position, where it is relative to other objects, remains the essential starting point for comprehending everything from simple motion to the cosmic dance of galaxies across the expanding universe. Distance represents one of the most essential concepts in physics, describing the length of path traveled between points in space. Unlike position, which specifies location, distance purely measures how far something has traveled, regardless of direction. This distinction becomes crucial when analyzing movement through space, whether tracking a satellite's orbit or measuring atomic interactions. Consider a vehicle traveling along a winding mountain road. If it begins at the base and follows the twisting route to the summit, the distance traveled equals the entire length of the road. Even if the car returns to exactly where it started, the total distance remains the entire journey's path length. This fundamental property distinguishes distance as a scalar quantity, having magnitude but no direction, separating it from vector quantities that include directional information. Distance measurements permeate our daily lives through familiar units like meters, kilometers, miles, and feet. These standardized measurements allow precise communication about spatial separation, whether describing the length of a room, the height of a mountain, or the depth of an ocean. The standardization of distance units revolutionized science, engineering, and commerce, allowing consistent measurements across different locations and times. Preparing and narrating this theory took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now back to the theory. In scientific applications, distance measurements span incredible ranges. Astronomers work with light years, about 9.5 trillion kilometers, to describe the vast separations between stars, while particle physicists measure subatomic structures in femtometers, 10 to the power of negative 15 meters. This scale flexibility makes distance a versatile concept applicable across all physical phenomena, from the quantum realm to cosmic structures. The precise measurement of distance has driven technological innovation throughout history. Ancient Egyptians developed sophisticated techniques to measure land boundaries after Nile floods. Medieval navigators used celestial observations to estimate distances at sea. Today, laser rangefinders can measure distances with sub-millimeter precision, while radar and LiDAR systems map terrain by measuring the time taken for electromagnetic signals to return after reflecting off distant objects. Distance calculations become more complex on curved surfaces. The shortest path between 2 points on a sphere, like Earth's surface, follows a great circle rather than a straight line. This geodesic principle explains why long-distance flights often follow curved paths on flat maps. Einstein's general relativity extends this concept further, showing that mass curves space-time itself, causing light to follow curved paths near massive objects, even though light always travels along the shortest possible route. The relationship between distance and time creates the foundation for measuring speed and velocity. Average speed equals distance divided by time, a simple ratio that quantifies how quickly objects move through space. This relationship becomes essential in everything from traffic management to spacecraft navigation, where precise distance measurements combined with accurate timekeeping enable velocity calculations that guide vehicles to their destinations. In quantum physics, distance takes on probabilistic properties that challenge classical intuition. The wavelength of a particle, the distance between successive peaks in its associated wave, determines many of its quantum behaviors. Electron orbitals in atoms represent probability distributions over distance rather than definite paths, with electrons more likely to be found at certain distances from the nucleus than others. These quantum properties of distance fundamentally shape atomic structure and chemistry. Medical technologies rely heavily on distance measurements at various scales. Ultrasound imaging calculates distances using sound wave reflections to create visual representations of internal structures. Computed tomography, CT, scans measure the distances X-rays travel through different tissues, while magnetic resonance imaging, MRI, maps the spatial distribution of hydrogen atoms throughout the body. Even simple stethoscopes function by transmitting sound across the distance between internal organs and the physician's ears. Distance measurements enable precise navigation that would astound previous generations. Global positioning systems triangulate position by measuring distances from multiple satellites, allowing devices to determine location with meter-level accuracy anywhere on Earth. Autonomous vehicles continuously measure distances to surrounding objects using cameras, radar, and LiDAR, building three-dimensional maps of their environments to navigate safely. The quantization of distance at the smallest scales represents one of physics' most profound discoveries. The Planck length, approximately 1.6 times 10 to the negative 35th meters, is theorized to be the smallest meaningful measurement of distance in the universe. Below this scale, the very concept of distance may break down, as quantum fluctuations in space-time become significant, potentially requiring entirely new mathematical frameworks to describe reality. In cosmology, the expansion of the universe stretches distance itself. Light from distant galaxies shows redshift because the space between emission and observation has expanded during the light's journey. This cosmic expansion means the distance between galaxies increases over time, even without the galaxies themselves moving through space in the conventional sense. This stretching of distance itself represents one of the most counterintuitive aspects of modern cosmology. Distance serves as the essential metric for spatial separation, providing the foundation for analyzing movement, designing structures, and understanding physical interactions at all scales. From the architect measuring building dimensions to the cosmologist mapping galactic distribution, distance remains one of physics' most fundamental and practical concepts. The measurement that tells us not just where things are, but how far apart they exist in our three-dimensional world. Mass defines the fundamental essence of matter, giving objects their substance and resistance to motion. Unlike weight, which depends on gravity's pull, mass remains constant, regardless of location. A bowling ball contains the same amount of matter, whether on Earth, the Moon, or floating in deep space. This intrinsic property distinguishes mass as an object's true physical presence in the universe. At its core, mass quantifies how much matter an object contains. A kilogram of lead and a kilogram of feathers contain identical amounts of mass, though they differ dramatically in volume and density. Mass isn't something objects possess. It's what makes them objects at all, providing the substantive reality we interact with daily. Without mass, the physical world as we know it couldn't exist. Mass manifests through two key properties. Inertial mass resists changes in motion, while gravitational mass generates and responds to gravitational forces. Einstein's equivalence principle established that these two manifestations of mass are identical, connecting the resistance to acceleration with the force of gravity in a profound insight that helped birth general relativity. The resistance aspect of mass explains why pushing an empty shopping cart requires less effort than a full one. The more mass an object contains, the greater the force needed to change its motion. This relationship forms the foundation of Newton's second law of motion, where force equals mass times acceleration. Without this resistance property, objects would accelerate infinitely from the slightest touch, making stable structures impossible. Gravitational attraction represents mass's other crucial manifestation. Every object with mass attracts every other massive object in the universe. This universal gravitation explains planetary orbits, falling objects, and cosmic structures. Unlike electromagnetic forces that can repel or attract, gravity always attracts, pulling masses together across the vastness of space. The force between two masses grows stronger as they become more massive and weakens as the distance between them increases. Mass shapes the universe's largest structures. Galaxies form around concentrations of dark matter, mysterious mass that doesn't interact with light but exerts gravitational influence. Galaxy clusters contain thousands of galaxies bound by mutual gravitational attraction, while on the grandest scales, the cosmic web of galaxy superclusters traces mass distribution throughout the observable universe. This hierarchical clustering demonstrates how mass organizes cosmic architecture across billions of light years. The measurement of mass varies depending on circumstances. Laboratory balances compare an object's mass to known standards through gravitational force, while in space, mass must be determined through inertial measurements by applying known forces and measuring acceleration. Whether using traditional scales or sophisticated inertial sensors, these measurements always quantify the same fundamental property: how much matter an object contains. Mass's relationship with energy revolutionized physics through Einstein's famous equation E equals mc squared. This equivalence revealed that mass and energy are interchangeable. Mass can transform into energy and vice versa. This principle explains the tremendous energy released in nuclear reactions, where small amounts of mass convert to enormous energy. The sun continuously transforms about 4 million tons of mass into energy every second through nuclear fusion, powering all life on Earth. At the subatomic level, mass becomes even more intriguing. The Higgs mechanism, confirmed by the discovery of the Higgs boson in 2012, explains how fundamental particles acquire mass. According to this theory, particles interact with the Higgs field, permeating all space, experiencing resistance that manifests as mass. Different particles interact with this field to different degrees, explaining their varying masses. Some particles, like photons, don't interact with the Higgs field at all, remaining massless and traveling at light speed. Beyond the standard model of particle physics lies the mystery of dark matter, mass that doesn't interact with electromagnetic forces, but reveals itself through gravitational effects. Astronomical observations indicate that ordinary matter comprises only about 15% of the total mass in the universe, with the remainder consisting of this invisible dark matter. Though we can't see it directly, its gravitational influence shapes galaxy formation and cosmic structure, demonstrating how mass affects the universe even when invisible. Mass also influences how we experience time. According to general relativity, massive objects curve space-time, causing time to pass more slowly in stronger gravitational fields. Clocks on GPS satellites run slightly faster than identical clocks on Earth because they experience weaker gravitational fields, requiring correction to maintain synchronization. This time, dilation effect, though tiny in everyday situations, becomes significant near extremely massive objects like black holes. The conservation of mass principles state that in closed systems, mass remains constant during ordinary chemical reactions and physical transformations. While Einstein's work showed that mass and energy are interchangeable, in practical situations below nuclear energy scales, mass conservation serves as an excellent approximation. This principle underlies chemistry, engineering, and countless natural processes, ensuring that matter cannot magically appear or disappear. Mass stands as one of physics' most fundamental concepts, the measure of matter's presence in the universe. It determines how objects resist motion, attract each other through gravity, and even bend the fabric of space-time itself. From the smallest particles to the largest galaxies, mass shapes the physical world, providing structure to existence and governing the cosmic dance of matter throughout the universe. Motion forms the essence of change in our universe. From subatomic vibrations to galactic rotation, nothing remains truly still. Even seemingly motionless objects experience atomic motion and participate in Earth's rotation and cosmic expansion. Motion represents not just movement, but the fundamental way the universe evolves over time. At its simplest, Motion describes an object's change in position relative to a reference point. This relativity proves crucial. Motion can only be measured by comparing positions across time. A passenger in a moving train may appear stationary relative to the train while moving rapidly relative to the ground. Both perspectives are equally valid, highlighting motion's dependence on the observer's frame of reference. Motion follows distinct patterns depending on the forces involved. Uniform motion occurs when an object travels at constant speed in a straight line, maintaining steady velocity in the absence of external forces. Non-uniform motion happens when speed or direction changes, creating acceleration or deceleration. The graceful arc of a thrown ball, the oscillation of a pendulum, and the elliptical orbit of planets all represent non-uniform motion shaped by consistent forces. Linear motion follows straight paths, while rotational motion occurs around an axis. Periodic motion repeats in regular cycles, like a clock's pendulum swinging back and forth. Chaotic motion, despite following deterministic rules, becomes unpredictable over time due to sensitivity to initial conditions, explaining weather patterns and turbulent fluids. Each motion type follows mathematical principles that allow prediction and analysis. Motion's predictability enabled early scientific breakthroughs. Galileo's studies of falling objects and pendulums challenged Aristotelian physics, while Kepler's laws described planetary motion with mathematical precision. Newton synthesized these insights into his laws of motion, creating a framework that accurately predicted everything from cannon trajectories to comet orbits. These laws remained unchallenged for centuries until Einstein's relativity addressed motion at extreme speeds and gravitational conditions. The measurement of motion requires tracking position changes over time. Modern technology employs diverse methods. Accelerometers in smartphones detect motion changes, radar measures vehicle speeds, and laser interferometers detect gravitational waves by measuring microscopic motions of suspended mirrors. These measurement techniques span from everyday applications to cutting-edge physics research. Motion's relationship with energy creates the distinction between kinetic energy, energy of motion, and potential energy, stored energy that can produce motion. A boulder perched on a hill possesses potential energy that converts to kinetic energy when rolling downward. This energy transformation underlies countless natural processes, from flowing rivers to chemical reactions. Relative motion creates fascinating effects that challenge intuition. The Doppler effect causes sound pitch or light color to shift depending on relative motion between source and observer, explaining why approaching sirens sound higher pitched than receding ones. At speeds approaching light, relativistic effects become significant. Time dilates, lengths contract, and mass increases relative to stationary observers. Quantum mechanics reveals motion's strange behavior at subatomic scales. Electrons don't follow defined trajectories around nuclei, but exist as probability clouds. Heisenberg's uncertainty principle demonstrates the fundamental impossibility of simultaneously knowing a particle's exact position and momentum, introducing inherent unpredictability to quantum motion. Brownian motion, the random movement of particles suspended in fluid, provided crucial evidence for atoms' existence. Einstein's analysis of Brownian motion showed how visible particle movement resulted from countless collisions with invisible molecules, helping convince skeptics about atomic theory's validity when observed experimentally. Motion analysis extends beyond physics to numerous applications. Biomechanics studies body motion to improve athletic performance and develop prosthetics. Civil engineers analyze structural motion to design earthquake-resistant buildings. Computer animators create realistic motion by implementing physics principles in their algorithms. Even medical imaging technologies like functional MRI track motion-related changes in blood flow to map brain activity. At cosmic scales, motion reveals the universe's history and fate. Galaxies' redshifts demonstrate universal expansion, while their rotational motion indicates dark matter's presence. Precise motion measurements of celestial bodies enable space missions to distant planets and reveal extrasolar planets through their gravitational effects on parent stars. Motion connects to every other physical concept. Without motion, forces would have nothing to act upon. Energy would have no way to transfer, and time would lose its meaning as change would cease. Understanding motion provides the foundation for comprehending the dynamic processes that shape our universe, from the smallest particles to the largest structures, revealing how change itself progresses through space and time. Speed measures how quickly an object moves from one location to another, representing the rate of distance covered over time. This fundamental metric differentiates between fast and slow movement, providing essential information about motion without indicating direction. At its mathematical core, speed equals distance divided by time. A car traveling 60 kilometers in 1 hour moves at 60 kilometers per hour regardless of its path or direction. This simplicity makes speed one of physics' most accessible concepts, introduced early in science education, yet remaining crucial in advanced applications. Unlike velocity, which specifies direction, speed only indicates magnitude. A vehicle circling a track maintains constant speed while continuously changing velocity due to directional shifts. This distinction classifies speed as a scalar quantity, having only magnitude, contrasting with vectors that possess both magnitude and direction. Speed ranges dramatically across nature. Human walking averages 5 kilometers per hour, while Olympic sprinters achieve 36 kilometers per hour. The fastest land animal, the cheetah, reaches 112 kilometers per hour in short bursts. These biological speeds pale compared to technological achievements. Commercial aircraft cruise at 900 kilometers per hour, while the Parker Solar Probe reached 586,800 kilometers per hour during its close solar approach, becoming humanity's fastest spacecraft. Cosmic speeds dwarf even these impressive figures. Earth orbits the Sun at approximately 107,000 kilometers per hour, while our solar system orbits the galactic center at 828,000 kilometers per hour. Light defines the universe's ultimate speed limit at 1.08 billion kilometers per hour, 300,000 kilometers per second. A cosmic speed limit that nothing with mass can reach, according to Einstein's relativity. Speed measurement techniques evolved throughout history. Ancient civilizations estimated speed by observing celestial motions or using water clocks to time journeys. Modern methods include radar guns employing Doppler effect, laser interferometry for precision measurements, and GPS systems calculating position changes over time. Particle accelerators measure subatomic particle speeds approaching light speed, while atomic clocks provide temporal precision necessary for extreme speed measurements. Context determines appropriate speed units. Everyday movement uses kilometers or miles per hour, while chemistry might measure reaction speeds in moles per second. Astronomy employs kilometers per second for planetary motion or percentages of light speed for cosmic phenomena. Computer processing speeds use operations per second, while communications measure data transfer in bits per second. All variations of the distance over time relationship, average speed versus instantaneous speed, highlights an important distinction. Average speed considers the entire journey, total distance divided by total time, while instantaneous speed measures motion at a specific moment. A car's speedometer displays instantaneous speed, constantly updating as conditions change, whereas average speed summarizes the entire trip. Terminal velocity represents the maximum speed an object reaches when falling through a fluid like air or water, where acceleration from gravity balances resistance forces. Skydivers reach terminal velocity of approximately 200 kilometers per hour in typical falling position, though specialized positions can increase or decrease this speed. Even raindrops have terminal velocities, explaining why gentle rain and destructive hail impact differently despite falling from similar heights. Wave propagation introduces another speed dimension. Sound travels through air at approximately 343 meters per second under standard conditions, but moves faster through denser media like water, 1,481 meters per second, or steel, 5,120 meters per second. These propagation speeds determine how quickly disturbances travel through materials without necessarily involving physical movement of the medium itself. Speed profoundly impacts everyday decisions. Traffic management, shipping logistics, and flight scheduling depend on accurately predicting movement speeds. Athletes and coaches analyze speed patterns to maximize performance. Engineers design vehicles, from bicycles to spacecraft, with speed considerations central to their function. Even manufacturing processes optimize production speeds to balance output quantity with product quality. Understanding speed enables prediction of arrival times, energy requirements for transportation, and collision forces. It connects distance and time, fundamental dimensions of physical reality, creating a concept that quantifies motion in meaningful, measurable terms across all scales of the universe. Velocity measures how quickly an object changes position in a specific direction, combining speed with directional information. This vector quantity proves essential for analyzing motion in physics, engineering, and everyday life. Unlike scalar speed, velocity requires both magnitude and direction. A car traveling 60 kilometers per hour eastward has a different velocity than one moving 60 kilometers per hour westward, despite identical speeds. This distinction becomes crucial when calculating how objects interact or predicting their future positions. Mathematically, velocity equals displacement divided by time. Displacement being the straight line distance and direction from starting point to ending point. This difference from speed becomes apparent in curved paths. A runner completing a circular track has traveled a considerable distance but experienced zero displacement, resulting in zero average velocity despite maintaining constant speed throughout. Velocity changes occur in two ways: speed alteration, fast or slower, or direction change, turning. Both represent acceleration, though we typically associate acceleration only with speed increases. A car rounding a curve at constant speed experiences acceleration because its velocity vector continuously changes direction. In navigation, velocity information enables precise position prediction. Ships, aircraft, and spacecraft continuously calculate velocity to determine future locations and make course adjustments. GPS systems track velocity changes to provide accurate arrival estimates and navigation guidance. The relative nature of velocity creates interesting phenomena. A passenger walking inside a moving train experiences different velocity relative to the train versus an observer on the ground. The passenger might walk at 5 kilometers per hour relative to the train, while moving at 105 kilometers per hour relative to the stationary observer if the train travels at 100 kilometers per hour. This velocity addition follows simple arithmetic at everyday speeds, but requires relativistic corrections near light speed. Sports analysis heavily utilizes velocity measurements. Baseball pitches reaching 160 kilometers per hour, tennis serves exceeding 240 kilometers per hour, and golf drives approaching 300 kilometers per hour demonstrate impressive human-generated velocities. Athletes and coaches analyze velocity vectors to optimize performance, using high-speed cameras and motion sensors to capture detailed movement data for technique refinement. Weather systems demonstrate velocity's importance in natural phenomena. Wind velocity, combining speed and direction, determines weather patterns, storm movement, and aviation conditions. Meteorologists track air mass velocities to predict weather changes, while storm chasers monitor tornado velocity to understand their behavior and improve warning systems. Ocean currents maintain distinct velocities affecting climate, marine ecosystems, and navigation. The Gulf Stream transports warm water at approximately 2 meters per second along North America's eastern coast, moderating Europe's climate. Understanding these current velocities helps explain marine species distribution, optimize shipping routes, and predict climate patterns. Terminal velocity represents the maximum velocity an object reaches when falling through a fluid like air, occurring when gravitational acceleration balances with fluid resistance. Skydivers typically reach terminal velocity around 55 meters per second, 200 kilometers per hour, in standard falling position, though this changes with body orientation and equipment. This physical limit explains why rain falls at consistent speeds, regardless of release height. Angular velocity measures rotational motion, describing how quickly an object rotates around an axis in radians per second. The Earth completes one rotation daily, giving it an angular velocity of 7.3 times 10 to the minus 5 radians per second. This concept applies to everything from spinning tops to planetary motion, connecting linear and rotational movement. Particle physics studies subatomic particles moving at extreme velocities approaching light speed. Particle accelerators like the Large Hadron Collider propel protons to 99.9999991% of light speed, revealing fundamental properties of matter through high-energy collisions. At these velocities, relativistic effects become significant, with particles experiencing time dilation and mass increase relative to stationary observers. Velocity analysis forms the cornerstone of mechanics, both classical and relativistic. From simple projectile trajectories to complex spacecraft maneuvers, understanding how objects move with specific speeds in particular directions allows us to predict control, and harness motion throughout the natural and engineered world. Acceleration describes how velocity changes over time, encompassing both speed variations and directional shifts. When a car accelerates from a standstill to highway speed, a spacecraft alters course, or a roller coaster rounds a loop. Acceleration is the physical quantity that quantifies these changes in motion. Mathematically, acceleration equals the rate of velocity change over time. Since velocity contains both magnitude and direction, acceleration occurs whenever either component changes. This makes acceleration a vector quantity with its own magnitude and direction. The standard unit is meters per second squared, m per s squared, representing velocity change per unit of time. Everyday acceleration experiences range from gentle to extreme. A typical passenger car accelerates from 0 to 100 kilometers per hour in about 8 seconds, averaging approximately 3.5 meters per second squared. High-performance sports cars achieve 0 to 100 kilometers per hour in under 3 seconds, exceeding 9 meters per second squared. By comparison, gravitational acceleration on Earth, known as g, equals approximately 9.8 meters per second squared downward, the acceleration experienced by falling objects when air resistance is negligible. Acceleration takes multiple forms in physical systems. Linear acceleration changes an object's speed along a straight path, like a sprinter leaving the starting blocks. Angular acceleration alters rotational velocity, as when a figure skater pulls in their arms to spin faster. Centripetal acceleration, directed toward the center of a circular path, maintains circular motion, despite inertia's tendency to continue straight-line movement. The human body detects acceleration rather than constant velocity, explaining why we feel movement when a vehicle starts, stops, or turns, but not during constant speed straight-line travel. This sensitivity stems from our vestibular system in the inner ear, where tiny fluid-filled chambers and sensory hairs detect acceleration, changes, and help maintain balance. Human acceleration tolerance varies by direction and duration. We withstand higher accelerations perpendicular to our spine, as in horizontal turns, then along it, vertical acceleration. Trained fighter pilots tolerate up to 9G using specialized techniques and equipment, while untrained individuals may lose consciousness at 5 to 6G. Rapid acceleration changes, called jerk, often cause discomfort even at lower magnitudes, explaining why smooth acceleration in luxury vehicles feels more comfortable than abrupt changes in economy models. Technological applications of controlled acceleration appear throughout engineering. Rockets continuously calculate acceleration to maintain optimal flight paths and fuel efficiency. Elevators limit acceleration to enhance passenger comfort. Even modern smartphone screens use accelerometers to detect device orientation and movement, enabling screen rotation and motion-based gaming. Negative acceleration, commonly called deceleration, occurs when objects slow down, such as braking vehicles or balls reaching maximum height during upward throws. Despite the separate term, deceleration simply represents acceleration in the opposite direction of motion, following identical physical principles. Gravitational acceleration reveals fascinating insights about astronomical bodies. Objects on the moon experience only 1.62 meters per second squared acceleration due to the moon's smaller mass, explaining the characteristic bouncing gait of Apollo astronauts. Jupiter's strong gravity produces 24.8 meters per second squared acceleration, nearly 2.5 times Earth's value. These variations affect everything from escape velocity calculations to the physical structures that could survive on different planets. Acceleration in curved spacetime leads to Einstein's revolutionary understanding of gravity. According to general relativity, mass curves spacetime, causing objects to follow geodesic paths that appear as acceleration. This equivalence between gravitational and inertial acceleration, where observers cannot distinguish between acceleration due to gravity and acceleration due to force, forms the foundation of modern gravitational theory. Particle accelerators use precisely controlled electromagnetic fields to produce extreme accelerations, propelling subatomic particles to near-light speeds for high-energy physics research. The Large Hadron Collider accelerates protons at approximately 10 to the power of 22 meters per second squared, allowing scientists to recreate conditions similar to those microseconds after the Big Bang and discover fundamental particles like the Higgs boson. Acceleration connects force and mass through Newton's second law. Force equals mass times acceleration, F equals ma. This relationship explains why identical forces produce different accelerations depending on an object's mass, a critical principle in countless applications from rocket propulsion to automotive engineering. Force creates, changes, or prevents motion throughout the universe. Nothing moves, stops, or alters course without force. From falling raindrops to shifting continents, all movement results from forces acting on objects. At its essence, force represents an interaction that pushes or pulls objects, causing changes in motion when unbalanced. Force operates through multiple forms. Gravitational force attracts masses. Electromagnetic force governs charged particle interactions. And strong and weak nuclear forces bind atomic nuclei despite proton repulsion. Force magnitude determines its effect's strength, measured in newtons, where 1 newton produces 1 kilogram meter per second squared acceleration. Force direction matters equally. Identical forces applied in different directions produce entirely different outcomes, making force a vector quantity requiring both magnitude and direction to fully describe. The relationship between force, mass, and acceleration forms Newton's second law, F equals ma. This equation reveals that identical forces produce different accelerations depending on mass. The more massive an object, the less it accelerates under given force. A push that easily moves a shopping cart barely affects a car, demonstrating this inverse relationship between mass and resulting acceleration. Contact forces require physical connection between objects. Friction opposes motion between surfaces, allowing walking, driving, and riding. Normal force prevents objects from passing through surfaces, pushing perpendicular to contact points. Applied force occurs whenever we physically push or pull objects, from opening doors to lifting weights. Non-contact forces act across distances without physical connection. Gravity pulls masses together, keeping planets orbiting stars and objects attached to Earth. Electrostatic force attracts or repels charged particles, enabling chemical bonds and static electricity effects. Magnetic force influences moving charges and magnetic materials, powering generators and motors. Forces exist in balanced or unbalanced states. Balanced forces produce no motion change, like two people pushing equally from opposite sides. Unbalanced forces create acceleration, with objects moving in the direction of the stronger force. This principle explains why heavier objects require greater force to achieve the same acceleration as lighter ones. Force appears in everyday phenomena. Walking pushes backward against the ground, which pushes forward on your feet. Throwing a ball transfers force through your arm to the ball. Stretching a rubber band stores potential energy that converts to kinetic energy when released. Every interaction involves forces transferring energy and changing motion. The measurement of force uses various instruments. Spring scales measure weight, gravitational force by compression or extension. Strain gauges detect minute deformations caused by forces on surfaces. Accelerometers measure resulting acceleration to calculate applied force when mass is known. Even pressure sensors indirectly measure force by detecting force distributed over areas. Force fields conceptualize how forces permeate space. Gravitational fields surround massive objects, affecting other masses within range. Electric fields emanate from charged particles, influencing other charges. These fields extend theoretically to infinity, though their strength diminishes with distance according to inverse square relationships. Understanding force revolutionized technological development, from simple machines like levers and pulleys that multiply force to complex engineering systems like bridges and skyscrapers that precisely balance diverse forces. Even rockets demonstrate Newton's third law, expelling exhaust gases backward to generate forward thrust. Force underlies countless natural processes. Plate tectonics reshape continents through enormous forces. Weather systems develop from pressure and temperature differentials. And living organisms contain molecular motors, exerting precise forces to enable movement and cellular function. Without force, the universe would remain motionless, a static collection of matter without change or development. Inertia governs how objects resist changes to their motion. This fundamental property of matter explains why moving objects continue moving and stationary objects remain at rest unless acted upon by an external force, shaping everything from daily experiences to cosmic events. Inertia stems directly from mass. The more massive an object, the greater its inertia and resistance to motion changes. This relationship explains why pushing a shopping cart requires less effort than moving a car, and why heavy vehicles need more powerful engines and stronger brakes than lighter ones. Newton formalized inertia in his first law of motion. Objects maintain constant velocity, including zero velocity for stationary objects, unless acted upon by an unbalanced force. This principle contradicted earlier Aristotelian physics, which incorrectly suggested that objects naturally come to rest without continuous force application. Inertia manifests in countless everyday situations. Passengers lurch forward when vehicles brake suddenly, as their bodies continue moving at the previous speed. Objects slide off car dashboards during turns because they maintain straight-line motion while the vehicle changes direction. Water remains in an inverted bucket, swung quickly in a vertical circle because its inertia overcomes gravity for brief periods. Safety engineering accounts for inertia extensively. Seatbelts prevent occupants from continuing forward during crashes. Airbags provide gradual deceleration to reduce injury from sudden stops. Even packaging materials like bubble wrap create space for fragile items to decelerate gradually rather than stopping instantly upon impact. Rotational inertia, moment of inertia, applies similar principles to rotating objects, determining resistance to rotational velocity changes. This property depends on both mass and mass distribution around the rotation axis. Figure skaters exploit this by pulling in their arms to reduce rotational inertia, causing dramatic spin acceleration without applying additional torque. Transportation systems rely heavily on inertia. Vehicles require energy to overcome inertia during acceleration, but once moving, inertia helps maintain motion with minimal additional energy input. This principle enables coasting and significantly improves fuel efficiency at constant speeds, particularly in massive vehicles like trains and ships, where inertia effects are substantial. Space exploration particularly demonstrates inertia's importance. In the vacuum of space, with negligible external forces, spacecraft maintain constant velocity without propulsion once desired speed is reached. Orbit adjustments require precise thruster firings to alter velocity vectors, after which inertia maintains the new trajectory indefinitely. The measurement of inertia typically occurs indirectly through force application and acceleration observation. Applying known force to an object and measuring resulting acceleration reveals its inertial mass, mathematically equivalent to gravitational mass, though conceptually distinct. Inertial frames of reference, non-accelerating reference frames where Newton's laws hold true, derive their name from this property. These reference frames provide the foundation for classical mechanics and serve as the basis for Einstein's special relativity, which addresses previously unexplained phenomena at extreme speeds. Inertial navigation systems utilize this property to determine position without external references. By precisely measuring acceleration in all directions and knowing initial position, these systems calculate current position through double integration, a technology crucial for submarines, spacecraft, and other vehicles operating where external navigation references are unavailable. At astronomical scales, inertia explains galactic structure and stellar formation. Gas clouds collapse under gravity, while inertia causes rotation, forming spinning disk galaxies rather than spherical clumps. Similarly, solar systems develop when collapsing nebulae conserve angular momentum, with inertia preventing all matter from falling directly into the forming star. Momentum represents motion's persistence and impact. It combines mass and velocity, explaining why moving objects carry forward motion and why collisions between objects of different sizes produce predictable outcomes. Mathematically, momentum equals mass multiplied by velocity. As a vector quantity, it has both magnitude and direction. A heavy truck moving slowly can have the same momentum as a smaller car moving quickly, though their effects differ significantly. Momentum's resistance to change explains why massive objects in motion are difficult to stop. A moving train requires tremendous braking distance due to its large momentum, while a baseball can be caught despite high velocity because of its relatively small mass. The conservation of momentum stands as one of physics' most fundamental principles. In isolated systems, total momentum remains constant unless external forces act. When billiard balls collide, their combined momentum before impact equals their total momentum afterward, though redistributed between the balls. Momentum transfer occurs during collisions. When a golf club strikes a ball, it transfers momentum, sending the ball flying while slightly slowing the club. This principle explains how hammers drive nails, bats hit baseballs, and vehicles experience impact forces during crashes. Elastic collisions preserve both momentum and kinetic energy. Bouncing billiard balls demonstrate this. They separate after collision with minimal energy loss. Inelastic collisions conserve momentum, but lose kinetic energy to deformation, heat, or sound, as when clay balls stick together upon impact. The impulse momentum theorem connects force and momentum change. Impulse, the product of force and time, equals momentum change. This explains why airbags extend collision time to reduce peak force, and why catching a baseball with a gloved hand extended forward reduces impact force compared to a rigid catch. In sports, momentum principles appear everywhere. Boxers roll with punches to extend impact time and reduce force. Baseball batters follow through after contact to maximize impulse delivered to the ball. Martial artists use opponents' momentum to execute throws with minimal effort. Rockets demonstrate momentum conservation dramatically. By expelling exhaust gases backward at high velocity, rockets generate forward thrust, even in the vacuum of space where there's nothing to push against. The total momentum of the rocket exhaust system remains constant. Angular momentum applies these concepts to rotating objects. Ice skaters spin faster when drawing their arms inward because angular momentum conservation requires increased rotation speed as mass moves closer to the rotation axis. Similarly, Earth's rotation remains steady because its angular momentum is conserved. At quantum scales, momentum becomes probabilistic through Heisenberg's uncertainty principle. The more precisely a particle's position is measured, the less precisely its momentum can be known, and vice versa. This fundamental limit isn't technological, but inherent to quantum systems. Relativistic momentum accounts for high-speed effects where classical momentum calculations fail. As objects approach light speed, relativistic effects become significant, requiring modified equations that incorporate mass increase relative to stationary observers. Impulse represents the cumulative effect of force applied over time, fundamentally connecting force with momentum change. When a baseball bat strikes a ball, a car crashes into a barrier, or a rocket engine fires, impulse determines the resulting change in motion. Mathematically, impulse equals force multiplied by the time during which it acts. This relationship, expressed as impulse equals force times time, provides critical insight. Identical momentum changes can occur through either strong forces applied briefly or weaker forces applied longer. The impulse momentum theorem formalizes this connection, stating that an object's momentum change equals the impulse applied to it. This relationship explains why airbags save lives during vehicle collisions. When a car crashes, occupants must decelerate from traveling speed to zero. Airbags extend this deceleration time compared to hitting the dashboard directly, reducing the peak force while delivering the same momentum-changing impulse. The longer deceleration time substantially reduces injury risk while achieving identical velocity change. Sports utilize impulse principles extensively. Baseball batters follow through after contact, extending the time of force application on the ball to increase impulse and hit distance. Golfers similarly extend their swing through and beyond the ball contact. Martial artists learn to prolong impact when delivering strikes for maximum effect and to absorb impulse gradually when receiving blows. The measurement of impulse often occurs indirectly through its effects. Ballistic pendulums measure bullet impulse by capturing fired projectiles and measuring the resulting swing amplitude. Force plates used in biomechanics research measure ground reaction forces over time during walking, running, or jumping, allowing calculation of the total impulse experienced during movement phases. Impulse magnitude significantly affects material behavior during collisions. The same total impulse delivered over different time frames can produce dramatically different outcomes. A hammer striking a glass window shatters it, while the same force applied gradually causes no damage. This time dependency explains why materials respond differently to sudden impacts versus gradual pressure. Rocket propulsion demonstrates impulse in sustained application. A rocket engine's performance is characterized by specific impulse, a measure of efficiency that represents the impulse delivered per unit of propellant mass. Higher specific impulse enables greater velocity change from the same amount of fuel, critical for spacecraft design. In mechanical engineering, impulse tolerance determines component durability. Structures must withstand both sustained loads and impulsive forces from impacts or vibrations. Engineers design shock absorbers, vibration dampers, and impact-resistant materials specifically to manage impulse by extending force application time and reducing peak forces. Medical applications include trauma assessment and prevention. Traumatic brain injuries result from sudden impulses to the head, where brain tissue experiences harmful acceleration due to skull impact. Protective equipment like helmets works by extending impact duration, reducing peak force, while absorbing the same total impulse. The controlled application of impulse enables precise movements in robotics and manufacturing. Industrial robots precisely control force application timing to handle delicate objects without damage. Surgical robots similarly apply calibrated impulses to perform procedures with minimal tissue trauma. Impulse appears in fluid dynamics when liquid or gas flow changes direction, creating pressure surges called water hammer in plumbing systems or pressure waves in pneumatic lines. These momentary pressure spikes represent the impulse required to change the fluid's momentum direction, potentially damaging pipes or equipment if not properly managed. The relationship between impulse and momentum highlights a fundamental aspect of nature. Physical interactions occur over time, not instantaneously. This temporal dimension of force application creates opportunities to manage interactions through timing control, whether minimizing damage during collisions or maximizing effectiveness in propulsion systems. Newton's laws of motion form the bedrock of classical mechanics, explaining how objects move and interact under applied forces. These three principles, first published in 1687 in Newton's Principia Mathematica, revolutionized physics and engineering, providing a framework that accurately describes countless physical phenomena, from falling apples to orbital mechanics. The first law, often called the law of inertia, states that an object at rest stays at rest, and an object in motion stays in motion with constant velocity, unless acted upon by an external force. This principle might seem obvious today, but it contradicted prevailing Aristotelian physics, which incorrectly suggested that objects naturally come to rest without continuous force application. This law explains countless everyday observations. A book remains motionless on a table until pushed. A hockey puck glides across ice until friction eventually stops it. Passengers lurch forward when a vehicle brakes suddenly, as their bodies maintain motion while the car slows down. Space probes travel for decades without propulsion, once launched into the vacuum of space where minimal external forces exist. The second law quantifies how force affects motion, stating that force equals mass times acceleration, F equals ma. This elegant equation reveals that the acceleration produced by a force depends on the object's mass. The same force produces greater acceleration in less massive objects. This relationship explains why pushing a shopping cart requires less effort than pushing a car, why heavy objects feel harder to get moving, and why identical engines produce different acceleration in vehicles of different weights. It allows precise calculation of forces needed for desired movements in everything from automotive engineering to rocket science. The third law establishes action-reaction pairs. For every action, there is an equal and opposite reaction. When you push against a wall, the wall pushes back with identical force. This reciprocal nature of forces explains how birds fly, pushing air downward while air pushes upward, how boats propel through water, and how rockets generate thrust by expelling exhaust gases. These three laws together form a coherent system for analyzing motion. The first law describes objects with no net force applied. The second law quantifies motion changes when forces are unbalanced. The third law explains how forces always occur in pairs between interacting objects. Newton's laws successfully predicted planetary orbits, projectile trajectories, and countless mechanical interactions with remarkable accuracy. Their application transformed engineering, enabling the Industrial Revolution through machines designed according to these principles. However, these laws have limitations. They apply precisely only at speeds much lower than light speed. Einstein's relativity theory later addressed high-speed scenarios where Newtonian physics produces incorrect predictions. Similarly, quantum mechanics was developed to explain atomic-scale phenomena, where classical mechanics fails. Despite these limitations in extreme conditions, Newton's laws remain essential for analyzing everyday physics and engineering situations. Aircraft designers, automotive engineers, architects, and countless other professionals apply these principles daily to create functional technology. The experimental verification of Newton's laws occurs continuously in both controlled laboratory settings and everyday life. From simple demonstrations of inertia to complex rocket launches, these principles consistently predict observable outcomes with impressive precision. Newton's insights built upon earlier work by Galileo and others, while establishing a comprehensive framework that dominated physics for centuries. Their elegant simplicity, distilling complex motion into three fundamental principles, demonstrates the power of scientific reduction and mathematical formulation in understanding natural phenomena. The practical applications of these laws extend beyond physics and engineering into unexpected fields. Sports science uses them to analyze athletic performance and equipment design. Medical professionals apply them to understand injury mechanics and rehabilitation. Even animation artists must understand these principles to create believable motion in virtual environments. Newton's laws connect to broader physical concepts as well. The conservation of momentum derives directly from the third law. Gravitational theory expanded on these principles to explain orbital mechanics. Even modern space exploration relies fundamentally on the same principles Newton formulated centuries ago. These laws fundamentally changed how humanity understands motion, replacing mystical or philosophical explanations with precise predictive principles. They represent one of science's greatest achievements, transforming observation into mathematical relationships that accurately describe and predict physical reality. Gravity represents perhaps the most immediately recognizable force in our daily lives, yet it remains among the most mysterious, fundamental interactions in physics. This universal attraction between masses shapes everything from falling objects to the structure of the entire cosmos. At its simplest level, gravity manifests as the familiar downward pull that keeps us anchored to Earth's surface. The acceleration due to gravity near Earth's surface equals approximately 9.8 meters per second squared, causing free-falling objects to increase their speed by this amount every second. This consistent acceleration explains why heavier objects don't fall faster than lighter ones in a vacuum. Their greater mass is exactly balanced by the proportionally greater gravitational force acting upon them. Understanding gravity underwent a revolutionary transformation through history. Ancient philosophers like Aristotle incorrectly believed heavier objects fall faster than lighter ones. Galileo challenged this view through experiments, though his famous Leaning Tower of Pisa demonstration may be apocryphal. Newton later formulated universal gravitation, recognizing that the same force causing apples to fall also keeps the moon in orbit around Earth. Newton's law of universal gravitation states that every mass attracts every other mass, with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. This inverse square relationship means that doubling the distance between objects reduces gravitational attraction to 1/4 of its original strength. This mathematical relationship accurately predicts orbital motion throughout the solar system. Einstein's general relativity transformed our understanding of gravity further, describing it not as a force but as the curvature of space-time caused by mass and energy. According to this view, massive objects like stars and planets warp the fabric of space-time, causing other objects to follow curved paths around them, similar to how a bowling ball placed on a stretched sheet causes smaller balls to roll toward it. This space-time curvature explanation successfully predicted phenomena that Newton's theory couldn't explain, including Mercury's orbital precession and the bending of light around massive objects like the Sun. The dramatic confirmation of light deflection during a 1919 solar eclipse provided crucial early evidence supporting Einstein's revolutionary theory. Gravity plays the dominant role in shaping cosmic structure across all scales. It causes interstellar gas and dust to collapse, forming stars and planetary systems. It binds stars together into galaxies and galaxies into clusters. The largest structures in the universe, vast filaments of galaxies stretching hundreds of millions of light years, formed through gravity's influence on the primordial universe. On Earth, gravity creates numerous familiar effects beyond simply keeping us grounded. It drives water downhill, creating rivers and shaping landscapes through erosion. It generates atmospheric pressure, with air molecules pulled toward Earth's surface. Even the circulation of our blood fights against gravity, requiring specialized valves to prevent backflow in our veins when standing. The relationship between mass and gravity remains proportional, but not identical. While an object's weight, the gravitational force acting upon it, changes depending on location, weighing less on the Moon than on Earth due to the Moon's smaller mass. Its intrinsic mass remains constant, regardless of location. An astronaut on the International Space Station appears weightless due to continuous freefall, but their mass remains unchanged. Gravitational strength varies slightly across Earth's surface due to our planet's rotation, which counters gravity slightly at the equator, and variations in crustal density. Precise gravity measurements help geologists locate underground mineral deposits, oil reservoirs, and other features that create measurable gravitational anomalies. Gravity's comparative weakness among fundamental forces presents a significant puzzle in physics. While it dominates at cosmic scales, gravity is approximately 10 to the 38th times weaker than the strong nuclear force binding atomic nuclei. This enormous discrepancy, known as the hierarchy problem, remains unexplained and suggests possible connections to extra dimensions or other exotic physics. The detection of gravitational waves in 2015 opened an entirely new observational window on the universe. These ripples in space-time, produced by violent cosmic events like colliding black holes, travel at light speed across the universe. Their detection required measuring distortions smaller than a proton's diameter, using laser interferometers with 4-kilometer-long arms, demonstrating both gravity's elusive nature and scientists' remarkable ingenuity. Attempts to reconcile gravity with quantum mechanics have created the greatest unsolved challenge in theoretical physics. While the other fundamental forces have successful quantum field theories, a complete quantum theory of gravity remains elusive despite decades of effort. Proposed solutions include string theory, loop quantum gravity, and other approaches that remain actively researched but experimentally unverified. The search for gravitational anomalies drives exploration of physics beyond the standard model. Observations of galactic rotation suggest the presence of dark matter, invisible mass, detectable only through gravitational effects. Similarly, the accelerating cosmic expansion attributed to dark energy may represent a modification to gravitational behavior at the largest scales, or an unknown energy permeating space. Free fall represents one of nature's purest manifestations of gravitational force. Objects moving solely under gravity's influence without resistance. This state reveals fundamental principles about gravity, motion, and the fabric of space-time itself. In its ideal form, free fall occurs when gravity acts as the only force on an object. Without air resistance or other impediments, all objects, regardless of mass, accelerate identically. This counterintuitive fact means that a feather and a bowling ball dropped simultaneously in a vacuum reach the ground at exactly the same time, both accelerating at 9.8 meters per second, squared, near Earth's surface. Galileo Galilei first challenged Aristotle's incorrect assertion that heavier objects fall faster than lighter ones. Though the famous Leaning Tower of Pisa demonstration may be legendary, Galileo's careful experiments with inclined planes established that falling rate depends on gravity alone, not on an object's mass. This revolutionary insight helped establish the scientific method and laid groundwork for Newton's later gravitational theory. The Apollo 15 mission dramatically demonstrated this principle on the Moon in 1971, when astronaut David Scott simultaneously dropped a hammer and feather in the lunar vacuum. Without air resistance, both objects struck the dusty surface simultaneously, confirming Galileo's insight in the most literal sense and demonstrating that this principle applies throughout the universe. Mathematically, free fall follows predictable equations of motion. On Earth, objects accelerate downward at approximately 9.8 meters per second squared, gaining this much speed every second. After 1 second, they reach 9.8 meters per second. After 2 seconds, 19.6 meters per second, and so on. Distance fallen increases according to the equation d equals 1/2 g(it) squared, where rg represents gravitational acceleration and t represents time. These simple relationships allow precise prediction of falling objects' position and velocity at any moment. Free fall creates the sensation of weightlessness, despite common misconception that astronauts in orbit experience zero gravity. In reality, the International Space Station orbits within Earth's substantial gravitational field, where gravity is only about 10% weaker than at the surface. Astronauts appear weightless because both they and their spacecraft continuously fall around Earth in a curved path that matches the planet's curvature, essentially in perpetual free fall. This equivalence between free fall and weightlessness formed the foundation for Einstein's insight that led to general relativity. His happiest thought came when he realized that a person in free fall would not feel their own weight. This equivalence principle, that gravitational acceleration is indistinguishable from acceleration due to other forces, led Einstein to reconceptualize gravity as curved space-time rather than a conventional force. Terminal velocity modifies pure free fall when objects move through atmospheres. As falling speed increases, air resistance grows until it balances gravitational acceleration, preventing further speed increase. This explains why raindrops hit Earth's surface at roughly 9 meters per second, regardless of the height from which they fall. Skydivers typically reach terminal velocity around 54 meters per second, 120 miles per hour, in traditional spread eagle position, though they can alter this by changing body position to modify air resistance. Free fall applications extend far beyond falling objects. Amusement park rides create brief, free fall experiences that produce the characteristic stomach-dropping sensation as internal organs temporarily float within the body. Drop towers provide scientists with valuable microgravity environments for experiments, generating several seconds of near-perfect free fall inside vacuum chambers to study phenomena without gravitational interference. Projectile motion represents a form of two-dimensional free fall, where objects launched horizontally or at an angle follow parabolic paths. The horizontal component of motion continues at constant velocity, while the vertical component accelerates downward due to gravity. This principle explains everything from thrown baseballs to artillery trajectories to the graceful arc of water from a fountain. The concept extends to orbital motion around celestial bodies. Satellites and moons essentially fall continuously around their primary bodies, with forward velocity precisely balanced, so they fall around the curve of the planet or star rather than into it. Even our solar system follows a free fall path around the Milky Way galaxy's center, completing one orbit every 230 million years. Measuring gravitational acceleration through free fall experiments has revealed subtle variations across Earth's surface. These variations occur due to differences in altitude. Greater distance from Earth's center reduces gravity slightly. Latitude, Earth's rotation, creates centrifugal effects that counteract gravity more strongly at the equator, and local geology. Denser underground formations increase gravitational pull slightly. These minute differences, typically in the range of 0.1%, provide valuable information about Earth's internal structure. In quantum mechanics, freefall takes on stranger properties. Quantum particles display wave-like characteristics during freefall, leading to phenomena like quantum interference in gravitational fields. Experiments with ultra-cold atoms in free fall have demonstrated quantum behaviors that blur the line between particle and wave, revealing deeper connections between quantum mechanics and gravity that researchers continue to explore. The extreme case of free fall occurs near black holes, where space becomes so curved that all paths lead inward past the event horizon. Once beyond this boundary, even light follows a one-way journey toward the singularity. This represents free fall in its most extreme manifestation, where space-time curvature becomes so severe that escape becomes impossible regardless of an object's velocity or composition. Energy fundamentally represents the ability to do work, to move objects, generate heat, or produce light. This capacity for causing change or transformation constitutes one of the universe's most essential properties, manifesting in countless forms that constantly convert between one another while always conserving the total amount. The concept of energy unifies diverse phenomena across physics. When a baseball player swings a bat, chemical energy stored in muscle tissues converts to kinetic energy in the moving bat. Upon striking the ball, some energy transfers to the ball's motion, while some dissipates as sound and heat. Despite these transformations, the total energy remains constant, demonstrating the conservation principle that underpins modern physics. Kinetic energy, the energy of motion, depends on both mass and velocity. A moving truck possesses more kinetic energy than a bicycle at the same speed due to its greater mass. Interestingly, doubling an object's mass doubles its kinetic energy, but doubling its velocity quadruples the energy, highlighting velocity's stronger influence. This relationship explains why highway accidents at higher speeds cause disproportionately greater damage. Potential energy exists in stored forms, ready to convert to kinetic energy under the right conditions. Gravitational potential energy increases with both height and mass. A boulder perched on a cliff has greater potential energy than the same boulder on a small hill. Elastic potential energy resides in stretched or compressed objects like springs and rubber bands. Chemical potential energy exists in molecular bonds, released during reactions like combustion or metabolism. The continuous transformation between potential and kinetic energy appears throughout nature. A pendulum swinging converts gravitational potential energy to kinetic energy at its lowest point, then back to potential energy at the extremes of its swing. Skateboarders in half-pipes experience the same principle, trading height, potential energy, for speed, kinetic energy, and back again with each oscillation. Thermal energy, often called heat, represents the microscopic kinetic and potential energy of particles in matter. Higher temperatures indicate faster moving particles with greater average kinetic energy. When objects of different temperatures contact each other, energy transfers from warmer to cooler regions until reaching thermal equilibrium. This heat transfer drives weather patterns, ocean currents, and countless industrial processes. Electromagnetic energy travels through space as photons, particles of light, carrying specific energy amounts determined by their frequency. Radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays constitute the electromagnetic spectrum, differing only in their energy levels. This energy form powers photosynthesis, enables wireless communication, and brings warmth from the distant sun across the vacuum of space. Nuclear energy originates from changes in atomic nuclei, either through fusion, combining light nuclei, or fission, splitting heavy nuclei. These processes convert tiny amounts of mass into enormous energy, as described by Einstein's E equals mc squared. The sun generates energy by fusing hydrogen into helium, while nuclear power plants harness energy from uranium fission. The mass energy equivalence principle demonstrates that matter itself represents highly concentrated energy. The measurement of energy uses the joule as its standard unit, defined as the energy transferred when applying a 1 Newton force through a 1 meter distance. Practical energy measurements often use derivatives like kilojoules for food calories or kilowatt hours for electricity consumption. Regardless of the scale, from subatomic particles to galactic clusters, energy measurements adhere to the same fundamental units and conservation principles. Energy quality affects its usefulness for performing work. High-quality energy forms, like electricity, can convert efficiently to other forms with minimal losses, while low-quality forms, like dispersed heat, have limited utility for driving further processes. This quality gradient explains why engines cannot be 100% efficient. Some energy always converts to less useful forms during operation, usually as waste heat. The steam engine's invention during the Industrial Revolution transformed human civilization by harnessing heat energy to perform mechanical work, though with efficiency limitations described by thermodynamics laws. The connection between energy and power, energy's transfer rate, creates another essential physical concept. While energy represents the total capacity for work, power measures how quickly that work occurs. A small engine and large engine might eventually perform the same amount of work, but the larger engine's higher power output completes the task faster. Power, measured in watts-joules per second, characterizes everything from light bulbs to rocket engines. Energy storage technologies demonstrate the practical applications of potential energy principles. Batteries store energy in chemical form, ready for conversion to electricity. Pumped hydro facilities store energy by pumping water to higher elevations during excess electricity production, then releasing it through turbines when demand increases. Flywheel systems store rotational kinetic energy, while capacitors store electrical potential energy in electromagnetic fields. Each method presents different efficiency, capacity, and discharge rate characteristics. The biological world depends entirely on energy transformations. Plants capture electromagnetic energy from sunlight through photosynthesis, converting it to chemical potential energy in carbohydrates. Animals obtain this stored energy by consuming plants or other animals, breaking down these molecules through respiration to power bodily functions. These metabolic processes transfer energy through complex biochemical pathways, ultimately enabling all biological activities from cellular maintenance to reproduction. Energy's role in technology has evolved dramatically throughout history. Early civilizations harnessed human and animal muscle power, supplemented by simple machines. Wind and water power enabled mills and basic manufacturing. Fossil fuels dramatically increased available energy during the Industrial Revolution, while the 20th century added nuclear energy and began developing renewable sources like modern solar and wind power. Each advance has increased human capability while presenting new environmental and resource challenges. Quantum mechanics reveals energy's fundamental quantization. It exists in discrete packets rather than continuous amounts. Electron energy levels in atoms can only take specific values, leading to characteristic spectral lines when electrons transition between states. This quantization extends to all energy forms at the smallest scales, contradicting classical physics' continuous energy model and leading to profound implications for understanding reality's fundamental nature. The interplay between energy, entropy, and information represents one of physics' most fascinating frontiers. Entropy, the measure of energy dispersion and disorder, always increases in isolated systems according to thermodynamics' second law. This directional flow from concentrated to dispersed energy forms, creates time's apparent arrow, and ultimately constrains all physical processes, from simple heat engines to complex living organisms. Information theory connects these concepts by relating energy requirements to information processing and storage, suggesting deep connections between physical energy and abstract information. Energy's conservation principle, that energy can neither be created nor destroyed, only converted between forms, stands as one of science's most thoroughly validated foundations. From subatomic particles to cosmic structures, every observation confirms this principle. Even in quantum mechanics, temporary energy loans allowed by the uncertainty principle must be repaid within strictly defined time limits. This principle provides the backbone for analyzing all physical systems, allowing scientists to track energy flows and transformations with confidence that the total remains constant, regardless of the process complexity. Work represents energy transfer that produces displacement or deformation. This fundamental concept bridges force and energy, quantifying how forces change physical systems over distances. Whenever you lift a book, stretch a spring, or compress a gas, work occurs as energy transfers through applied force. Mathematically, work equals force multiplied by displacement in the force's direction, expressed as W equals F dot D dot cos theta, where theta represents the angle between force and displacement vectors. This elegant relationship reveals several key insights. Work requires both force and displacement. Maximum work occurs when force aligns with movement direction, and no work occurs when force acts perpendicular to movement, regardless of magnitude. This perpendicular relationship explains why holding a heavy object stationary performs zero work despite requiring effort. Though your muscles expend chemical energy and fatigue, from physics' perspective, no work occurs without displacement. Similarly, a satellite orbiting Earth experiences gravitational force, but no work from gravity, since the force acts perpendicular to orbital motion. Work's units, joules, directly connect to energy, with 1 joule representing the work performed when a 1 Newton force moves an object 1 meter in the force direction. This equivalence between work and energy units reflects their fundamental connection. Work transfers energy between objects or converts between energy forms during physical processes. Positive work occurs when force components align with displacement direction, increasing the object's energy. Pushing a cart forward performs positive work, adding kinetic energy to the cart. Negative work happens when force opposes motion, reducing the object's energy. Brakes perform negative work on vehicles, converting kinetic energy to thermal energy through friction. Work manifests throughout mechanics in various forms. Lifting objects performs work against gravity, converting chemical energy from muscles to gravitational potential energy in the raised object. Compressing springs performs work that stores elastic potential energy. Accelerating vehicles performs work that increases kinetic energy. In each case, work serves as the mechanism for energy transfer between forms. The work-energy theorem formalizes this relationship, stating that net work performed on an object equals its kinetic energy change. This powerful principle enables analyzing complex motion by focusing on initial and final states rather than tracking detailed path dynamics. For example, calculating a roller coaster's speed at different points becomes straightforward by applying conservation principles and the work-energy relationship. Mechanical advantage through simple machines demonstrates work's practical applications. Levers, pulleys, and inclined planes reduce required force by increasing displacement, while the work remains constant, excluding friction losses. A pulley system might have the force needed to lift a weight, but doubles the rope distance pulled. This trade-off between force and distance maintains constant work, illustrating that machines cannot create energy but can make tasks more manageable by redistributing force requirements. Work analysis extends beyond mechanics to thermodynamics, where it describes energy transfers between systems. A gas expanding against a piston performs work on the surroundings, while compressing the gas requires work input. These processes form the foundation for heat engines, refrigerators, and countless industrial applications where work converts between thermal and mechanical energy forms. Thermodynamic work appears in various forms beyond simple mechanical displacement. Electrical work transfers energy when charges move through potential differences. Surface tension work occurs when liquid surfaces expand or contract. Chemical work happens during reactions that form or break molecular bonds. Each represents energy transfer through forces acting across distances, maintaining work's consistent definition across different domains. The distinction between conservative and non-conservative forces creates important work differences. Conservative forces like gravity and elastic forces perform path-independent work. The energy transfer depends only on initial and final positions. Non-conservative forces like friction perform path-dependent work, generally converting mechanical energy to thermal energy that dissipates into the environment. This distinction explains why perpetual motion machines remain impossible. Non-conservative forces like friction inevitably convert ordered energy into less useful thermal energy during any cyclic process. Without external energy input, systems eventually lose all useful energy to these dissipative processes, reinforcing thermodynamics' second law. Work measurement occurs through various methods, depending on the application. Force sensors combined with displacement measurements directly calculate mechanical work. Pressure volume diagrams represent work in thermodynamic cycles as the area enclosed by process curves. Power meters measure electrical work by tracking voltage, current, and time. Each approach quantifies energy transfer through different work forms while maintaining consistent underlying principles. Biological systems perform work continuously at various scales. Muscles convert chemical energy from ATP into mechanical work that moves body structures. Heart tissue performs work by pumping blood against pressure gradients. Molecular motors transport materials within cells by performing work at the nanoscale. These biological work processes share the same fundamental principles as macroscopic systems, though optimized through evolutionary processes for specific functions. The analysis of work and energy transfer revolutionized engineering during the Industrial Revolution. Early steam engines converted thermal energy from burning coal into mechanical work, with steadily improving efficiency. Modern power plants extend this concept with sophisticated thermodynamic cycles that maximize useful work extraction from heat sources. Transportation systems similarly evolved to increase work output efficiency, from early steam locomotives to modern electric vehicles. The concept of work efficiency, useful work output, divided by total energy input, drives countless technological improvements. Internal combustion engines convert only about 20 to 30% of fuel energy into useful mechanical work, with the remainder lost as heat. Electric motors achieve much higher efficiencies, often exceeding 90%, by eliminating many dissipative processes. This efficiency difference highlights why energy conversion pathways matter significantly in engineering applications. Economic systems implicitly incorporate work concepts through energy resource valuation. Industries converting energy into useful work form civilization's backbone, from electrical generation to manufacturing to transportation. The economic value of different energy sources partly reflects their capacity for performing useful work versus energy losses during conversion and transmission processes. Virtual work principles extend traditional work concepts to analyze mechanical equilibrium. By examining how systems would respond to hypothetical displacements, engineers can determine force distributions in complex structures without solving complete equations of motion. These powerful mathematical techniques underlie modern structural analysis software used in designing everything from bridges to aircraft. The relationship between work, energy, and information processing appears in computing systems. Computers perform work at the microscopic level when moving electrons through circuits, with this work enabling information processing and storage. Theoretical limits on computing efficiency derive from thermodynamic work principles, establishing minimum energy requirements for information manipulation and helping explain why computers generate heat during operation. Work's central position in physics connects seemingly disparate concepts into a coherent framework, from simple mechanical operations to complex biological processes, from industrial machinery to information technology. Work provides the essential link between force application and energy transfer. Understanding work enables analyzing, predicting, and optimizing how energy flows through systems, establishing it as one of physics' most practical and fundamental concepts. Power measures energy transfer rate, the speed at which work occurs or energy converts between forms. Unlike energy, which represents capacity for causing change, power quantifies how quickly that change happens. This distinction matters tremendously in practical applications, explaining why power specifications feature prominently in everything from light bulbs to aircraft engines. Mathematically, power equals work divided by time or energy transferred per unit time. The standard measurement unit, the watt, represents 1 joule per second, a seemingly small amount that quickly scales to kilowatts, 1,000 watts, and megawatts, 1,000,000 watts, in common applications. This mathematical relationship illuminates why identical energy amounts can produce dramatically different effects depending on delivery time. The energy in a gallon of gasoline released instantly creates an explosion, while the same energy released gradually powers a vehicle for many miles. Power manifests throughout nature across extraordinary ranges. A hummingbird's metabolism generates about 0.1 watts during rest, while human bodies typically produce 100 watts during normal activity and up to 2,000 watts during maximum exertion. Large wind turbines generate around 5 megawatts in favorable conditions, while large nuclear reactors produce over 1,000 megawatts continuously. The sun dwarfs these figures, radiating approximately 3.8 times 10 to the 26th watts, with about 1.7 times 10 to the 17th watts reaching Earth. Mechanical power appears whenever forces cause movement. A car engine's power determines its acceleration capability. Higher power engines increase speed more rapidly, even in identical vehicle masses. This explains why automotive specifications include both horsepower, 1 horsepower equals 746 watts, and torque, with power increasing proportionally with rotational speed while torque may remain constant. The relationship between force, velocity, and power, P equals F times V, emphasizes that both aspects matter. Strong force applied slowly can deliver the same power as weaker force applied quickly. Electrical power, calculated as voltage multiplied by current, P equals VI, provides perhaps the most familiar power application in daily life. Household devices display power ratings indicating energy consumption rates, from 10-watt LED bulbs to 1,500-watt hair dryers. These ratings determine electricity costs, circuit load requirements, and heat generation during operation. High-voltage transmission lines reduce energy losses by decreasing current requirements for equivalent power delivery, demonstrating power delivery optimization in practical systems. The distinction between average and instantaneous power creates important practical differences. Electronic devices often list both maximum and typical power consumption, with maximum figures determining cooling and electrical supply requirements, while typical figures help estimate operating costs. Modern electronics frequently include sophisticated power management systems that continuously adjust consumption based on demand, significantly improving efficiency compared to older, constant power designs. Thermodynamic power analysis forms the foundation for engines, power plants, and energy conversion systems. Thermal efficiency, useful power output divided by fuel power input, typically ranges between 25 to 60% for most heat engines, with theoretical maximum efficiency determined by temperature differences according to Carnot's principles. Improving power plant efficiency by even small percentages can yield enormous economic and environmental benefits when applied to gigawatt-scale facilities operating continuously. Human body power output illustrates fascinating biological limitations and adaptations. Muscles can generate approximately 100 watts of sustained power through aerobic metabolism, with elite athletes maintaining 300 to 400 watts during endurance events. Brief anaerobic efforts can produce over 2,000 watts, but only for seconds before exhaustion occurs. These power output limitations influenced historical technology development, from animal domestication to mechanical advantage devices like pulleys and levers. Power transmission introduces additional considerations beyond generation capacity. Mechanical power transmits through shafts, belts, and gears, with losses from friction and deformation. Hydraulic systems transmit power through pressurized fluid, enabling force multiplication and flexible routing. Electrical transmission through conductors encounters resistance losses that increase with distance, requiring voltage transformation for efficient long-distance power delivery. Each transmission method presents different efficiency, weight, flexibility, and reliability characteristics suitable for specific applications. Electric power generation exemplifies large-scale power conversion technology. Modern power plants convert primary energy sources, chemical, nuclear, solar, wind, hydro, into electrical power through various intermediate stages. Gas turbines convert fuel chemical energy to mechanical shaft rotation through combustion, which generators then convert to electrical power. This multiple conversion process introduces efficiency losses at each stage, explaining why thermal power plants typically achieve only 30 to 40% overall efficiency despite using highly optimized components. Peak power versus sustained power creates critical design considerations in many systems. Electric vehicles must manage battery discharge rates to balance acceleration, performance, peak power against driving range energy capacity. Spacecraft power systems distinguish between average power for normal operations and peak demands during maneuvers or equipment activation. Computer processors implement turbo boost modes for temporary performance increases while maintaining sustainable thermal design power during continuous operation. Power density, power output per unit volume or mass, often limits system performance more than absolute power capability. Mobile applications like aircraft engines, power tools, and portable electronics prioritize high power density to minimize weight. Stationary applications like power plants can utilize lower power density solutions when space and weight constraints are less restrictive. These density considerations explain why different applications use dramatically different power generation technologies despite serving similar functions. Power measurement techniques vary across applications. Mechanical dynamometers measure rotational power by applying controlled loads to rotating shafts and measuring torque and speed. Electrical power meters monitor voltage and current, calculating instantaneous and cumulative power consumption. Calorimetric methods determine power by measuring heat generation rates, particularly useful for systems where direct measurement proves difficult. These diverse approaches enable precise power quantification across fields, from automotive testing to utility billing. The relationship between power and efficiency drives technological advancement. Higher efficiency systems require less input power for equivalent output, reducing resource consumption, operational costs, and environmental impact. This principle explains the transition toward more efficient technologies like LED lighting, which produces equivalent illumination to incandescent bulbs while consuming 85% less power. Similar efficiency improvements appear throughout modern technology, from high-efficiency furnaces to energy-optimized computing systems. Renewable power generation introduces variability challenges absent in conventional power systems. Solar and wind power fluctuate with weather conditions, requiring energy storage or supplemental generation to maintain consistent supply. This intermittency creates grid management challenges, but also drives innovation in smart grid technologies, demand response systems, and energy storage solutions that collectively accommodate variable power generation while maintaining reliable service. Power limitations often constrain technological capabilities more than total energy availability. Space missions carefully budget power consumption among instruments, communication systems, and life support, frequently determining which experiments can operate simultaneously. Mobile devices implement aggressive power management to extend battery life while maintaining essential functions. Even biological organisms constantly balance power expenditure across competing needs like locomotion, digestion, and reproduction based on available metabolic power generation. The analysis of power flows through systems enables optimization across diverse applications. Transportation engineers evaluate vehicle power requirements across different speeds and conditions to design appropriate drivetrains. Building designers model power consumption patterns to properly size HVAC systems and electrical infrastructure. Process engineers analyze manufacturing power requirements to identify efficiency improvement opportunities. These analytical approaches transform power from abstract physics concept to practical engineering parameter. Power's fundamental role in physics connects energy to time, arguably the two most essential concepts in physical science. This relationship enables quantifying not just what changes occur through energy transfers, but how rapidly these changes happen, creating a critical dimension for analyzing and optimizing systems across scales from quantum processes to cosmic phenomena. Heat represents energy transfer between objects due to temperature differences. Unlike other energy forms with visible effects like motion or electricity, heat flows invisibly, yet governs countless phenomena, from weather patterns to industrial processes. This fundamental energy mode drives thermodynamics, the branch of physics governing energy transformation and transfer. At its microscopic foundation, heat represents the kinetic and potential energy of randomly moving particles within matter. Higher temperature corresponds to faster average particle motion and greater vibration amplitudes. When objects at different temperatures contact each other, this microscopic motion transfers from warmer regions, faster moving particles, to cooler regions, slower moving particles, until reaching thermal equilibrium, equal temperatures throughout the system. Heat transfer occurs through three primary mechanisms: conduction, convection, and radiation. Conduction transfers heat through direct molecular contact without bulk material movement. This process dominates in solids, where molecules vibrate more vigorously at higher temperatures, transferring energy to neighboring molecules through collisions. Metals conduct heat particularly effectively because their free electrons move rapidly through the material, transferring energy efficiently between locations. Convection transfers heat through fluid movement, carrying thermal energy between regions. Natural convection occurs when temperature differences create density variations that drive fluid flow. Hot air rises while cooler air descends, creating circulation patterns. Forced convection utilizes external mechanisms like fans or pumps to enhance fluid movement and accelerate heat transfer. This mechanism explains why wind makes cold days feel colder through increased convective cooling of skin surfaces. Radiation transfers heat through electromagnetic waves that require no medium for propagation. All objects above absolute zero emit thermal radiation, with emission intensity and wavelength spectrum depending on temperature. Higher temperatures produce more intense radiation at shorter wavelengths. This mechanism enables the Sun to warm Earth across 93 million miles of vacuum and explains why you feel warmth near a fire, even without direct airflow from the flames to your skin. The measurement of heat utilizes several related but distinct units. The joule represents heat's fundamental unit as a form of energy. The calorie, historically defined as the heat required to raise 1 gram of water by 1 degree Celsius, remains common in nutritional contexts, with food calories actually representing kilocalories. British thermal units, BTUs, appear in heating and cooling applications, particularly in regions using imperial measurement systems. These diverse units reflect heat's role across multiple scientific and engineering domains. Heat capacity, the energy required to raise an object's temperature by 1 degree, varies dramatically between materials and explains their different thermal behaviors. Water possesses exceptionally high specific heat capacity, 4.18 joules per gram per degree Celsius, requiring substantial energy to warm and releasing considerable energy when cooling. This property moderates Earth's climate by allowing oceans to store enormous heat quantities during summer and release it gradually during winter, while also making water excellent for cooling systems and thermal storage applications. Latent heat reveals another crucial thermal phenomenon: energy required for phase changes without temperature change. Water absorbs approximately 334 joules per gram when melting from ice to liquid while maintaining 0 degrees Celsius, and 2,260 joules per gram when vaporizing from liquid to steam at 100 degrees Celsius. These substantial energy requirements explain ice's cooling effectiveness, absorbing heat during melting, and why steam burns cause severe injuries, releasing enormous energy during condensation on skin. The distinction between heat and temperature creates crucial scientific clarity. Heat represents energy transfer, while temperature indicates average particle kinetic energy regardless of quantity. A cup of boiling water contains less thermal energy than a bathtub of warm water despite its higher temperature. This distinction explains why ocean temperatures change more slowly than land temperatures during seasonal transitions. Their vastly different heat capacities require different energy quantities for equivalent temperature changes. Thermodynamics laws formalize heat's fundamental properties. The first law, energy conservation, states that energy transfers between forms, but neither creates nor destroys total energy. The second law establishes heat's directional nature, spontaneously flowing from warmer to cooler objects, never the reverse without external work input. The third law establishes absolute zero as the theoretical temperature limit, where molecular motion minimizes. These principles collectively govern all thermal processes from simple conduction to complex phase transitions. Heat engines, devices converting thermal energy to mechanical work, drive civilization's technological infrastructure. Internal combustion engines, steam turbines, and jet engines all operate by harnessing temperature differences to perform useful work, with efficiency fundamentally limited by the temperature ratio between hot and cold reservoirs, according to Carnot's principle. This theoretical limit explains why engineers continually seek higher operating temperatures in power generation systems to improve efficiency. Thermal management represents a critical engineering discipline affecting numerous applications. Electronics generate heat during operation that must dissipate to prevent component damage. Buildings require heating and cooling systems that balance comfort with energy efficiency. Industrial processes often generate excess heat that can either create problems requiring mitigation or opportunities for recovery and utilization. These applications employ heat exchangers, devices transferring heat between fluids without mixing, in configurations ranging from simple radiators to complex multi-stage systems. Biological systems have evolved sophisticated heat management mechanisms. Warm-blooded animals maintain constant internal temperatures through metabolic heat generation and regulatory systems like sweating, panting, or shivering. Cold-blooded creatures adapt behavior to environmental conditions, seeking sun or shade to regulate body temperature. Even plants manage heat through transpiration, water evaporation that provides cooling effects similar to sweating. These diverse strategies highlight thermal regulation's fundamental importance to life. Geothermal heat, Earth's internal thermal energy from radioactive decay and residual formation heat, drives numerous geological processes. This heat creates convection currents in the mantle that drive plate tectonics, volcanic activity, and mountain formation. Human applications harness this heat through geothermal power plants, generating electricity from high-temperature underground reservoirs and ground-source heat pumps, utilizing stable subsurface temperatures for building climate control. Climate science fundamentally studies heat distribution and transfer on planetary scales. Greenhouse gases alter atmospheric heat radiation properties, affecting global temperature by allowing sunlight to enter while partially blocking infrared radiation from escaping. Ocean currents redistribute heat from equatorial to polar regions, moderating temperature extremes. Understanding these heat transfer mechanisms proves essential for modeling climate systems and evaluating potential future changes. Cryogenics, the study and application of extremely low temperatures, reveals heat's behavior near absolute zero, 273.15 degrees Celsius. At these temperatures, materials exhibit extraordinary properties, including superconductivity, zero electrical resistance, superfluidity, zero viscosity, and quantum effects typically obscured at higher temperatures. Practical applications include medical imaging systems, particle accelerators, and certain quantum computing implementations, all requiring sophisticated heat management to maintain ultra-low temperatures. Thermal imaging technology detects infrared radiation to visualize temperature differences invisible to the naked eye. Applications range from building energy audits, identifying heat leaks, to medical diagnostics, detecting inflammation through skin temperature, differences to search and rescue operations, locating people in darkness or through smoke. These technologies leverage understanding of black-body radiation principles to quantify temperature from detected infrared intensity patterns. Heat's universal presence through matter and essential role in energy transfer establishes it as one of physics' most fundamental and practically important concepts. From molecular motion to global climate, from industrial processes to biological systems, heat flows constantly shape our world's behavior across all scales, making thermal physics central to understanding natural phenomena. and developing sustainable technological solutions. Temperature measures the thermal energy intensity in matter, indicating the average kinetic energy of particles rather than total energy content. This distinction explains why a match flame at 1500 degrees Celsius can easily burn your finger despite containing less total energy than a bathtub of warm water at 140 degrees Fahrenheit, 40 degrees Celsius. Temperature represents one of our most commonly measured physical properties, influencing countless natural processes and technological applications. At the molecular level, temperature directly corresponds to particle motion. Higher temperatures indicate greater average kinetic energy. Molecules move faster, vibrate more vigorously, and rotate more rapidly. In gases, molecules travel freely with average speeds directly proportional to temperature. In liquids, molecules maintain close proximity while still flowing past one another. In solids, atoms primarily vibrate around fixed positions, with amplitude increasing at higher temperatures. These microscopic behaviors collectively create the macroscopic property we experience as temperature. Temperature measurement has evolved significantly throughout history. Early methods relied on subjective sensation, hot, warm, cool, cold, until the development of thermoscopes in the 16th century that displayed relative temperature changes through fluid expansion. Modern temperature scales emerged with Fahrenheit's mercury thermometer in the early 18th century, followed by Celsius's scale, using water's freezing and boiling points as references. The scientific community primarily uses the Kelvin scale, which shares Celsius's degree size, but begins at absolute zero, the theoretical minimum temperature where particle motion reaches its quantum limit. The relationship between different temperature scales follows simple conversion formulas. Celsius to Fahrenheit, degrees Fahrenheit, equals degrees Celsius, times 9/5 plus 32. Celsius to Kelvin, Kelvin equals degrees Celsius, plus 273.15. These conversions enable scientists and engineers worldwide to communicate thermal conditions precisely regardless of regional measurement traditions. While Fahrenheit remains common in everyday use in some countries, scientific research universally employs Celsius or Kelvin to maintain consistency across disciplines and national boundaries. Temperature's effects on matter create three primary phase states: solid, liquid, and gas, with transitions occurring at specific temperatures depending on pressure and chemical composition. Water exemplifies these transitions with freezing at 0 degrees Celsius and boiling at 100 degrees Celsius under standard atmospheric pressure. These phase transitions represent energy absorption or release, latent heat, without temperature change, creating thermal plateaus that stabilize temperatures in many natural and engineered systems. Temperature differences drive heat transfer, always flowing from warmer to cooler regions until reaching thermal equilibrium. This directional flow represents a fundamental aspect of thermodynamics' second law. Entropy increases in isolated systems as temperature differences diminish over time. The rate of heat transfer depends on both the temperature difference magnitude and the thermal properties of involved materials, with greater differences producing faster energy transfer. Materials respond to temperature changes in various ways beyond phase transitions. Thermal expansion causes most substances to increase in volume as temperature rises. This property enables thermometers to function using expanding liquids, but also requires engineering solutions like expansion joints in bridges and railways to accommodate dimensional changes across temperature variations. Some specialized materials even exhibit negative thermal expansion, contracting when heated, a property useful in precision instruments and specialized applications. Temperature significantly affects material properties beyond dimensions. Electrical conductivity typically decreases in metals, but increases in semiconductors as temperature rises. Mechanical properties like strength, ductility, and hardness often decrease at higher temperatures, explaining why metals become easier to shape when heated. Chemical reaction rates generally increase with temperature, approximately doubling with each 10 degrees Celsius increase. The principle behind refrigeration, preserving food by slowing bacterial growth and chemical deterioration. Temperature regulation plays a crucial role in biological systems. Mammals and birds maintain nearly constant internal temperatures through homeostatic mechanisms, despite environmental fluctuations. This thermal regulation enables enzymes and biochemical processes to operate within narrow optimal temperature ranges, supporting complex biological functions. Human body temperature averages approximately 37 degrees Celsius, 98.6 degrees Fahrenheit, with even small variations causing significant physiological effects. Fevers above 40 degrees Celsius, 104 degrees Fahrenheit, potentially causing protein denaturation and brain damage. Environmental temperature variations drive weather patterns and climate systems. Temperature differences between equatorial and polar regions create atmospheric and oceanic circulation patterns that distribute heat globally. Daily temperature cycles result from solar heating and nighttime radiative cooling, while seasonal variations occur due to Earth's axial tilt, changing solar intensity throughout the year. These natural temperature patterns significantly influence agriculture, ecology, and human settlement patterns worldwide. Temperature extremes in nature span an extraordinary range. The lowest natural temperature recorded on Earth's surface reached negative 89.2 degrees Celsius, negative 128.6 degrees Fahrenheit, in Antarctica, while the highest authenticated air temperature reached 56.7 degrees Celsius, 134.1 degrees Fahrenheit, in Death Valley, California. Deep ocean hydrothermal vents can exceed 400 degrees Celsius without boiling due to extreme pressure, supporting unique ecosystems adapted to these conditions. Beyond Earth, temperatures range from below 3 Kelvin in deep space to millions of degrees in stellar cores and billions in supernova explosions. Technological applications routinely create temperatures far beyond natural terrestrial ranges. Industrial furnaces reach thousands of degrees for metallurgical processes, while cryogenic systems approach absolute zero for scientific research and specialized applications. Particle accelerators generate plasma exceeding 10 million Celsius, temporarily creating conditions similar to the early universe moments after the Big Bang. These extreme temperatures enable materials processing, scientific research, and engineering applications impossible under ambient conditions. Temperature sensing technologies employ diverse physical principles. Thermocouples use voltage generated at junctions between different metals. Resistance temperature detectors measure conductivity changes. Thermistors use semiconductor resistance variations, and infrared sensors detect thermal radiation without contact. Advanced applications employ quantum effects like superconducting transitions for extremely precise measurements. These diverse technologies enable temperature monitoring across applications, from cooking to industrial processes to scientific research with appropriate sensitivity and range. The concept of negative absolute temperature presents an intriguing theoretical construct for specific quantum systems. Unlike conventional negative temperatures, which simply indicate colder than zero on Celsius or Fahrenheit scales, true negative absolute temperatures represent states where adding energy decreases entropy, essentially systems hotter than infinite temperature. These exotic states occur in carefully prepared quantum systems with bounded energy distributions and remain an active research area in quantum thermodynamics. Global temperature monitoring forms the cornerstone of climate science. Systematic surface temperature measurements began in the mid-1800s, with satellite measurements adding global coverage since the late 20th century. These records document global average temperature increases of approximately 1.1 degrees Celsius since pre-industrial times, providing essential data for understanding climate change mechanisms and projecting future conditions. This temperature record represents one of science's most scrutinized and verified datasets due to its significance for environmental policy and planning. Temperature calibration ensures measurement accuracy through comparison with known reference points. Primary standards include phase transitions of pure substances under controlled conditions, like water's triple point, 0.01 degrees Celsius, where solid, liquid, and vapor coexist in equilibrium. Secondary standards include certified reference thermometers calibrated against primary standards. This calibration hierarchy ensures temperature measurements remain consistent and accurate across scientific and industrial applications worldwide. Temperature's role as a fundamental physical property permeates virtually every aspect of natural science and technology, from determining molecular motion to driving global weather patterns, from enabling precise metallurgical processes to supporting complex biological systems. Temperature influences matter's behavior across all scales. Understanding temperature, both its measurement and effects, remains essential for fields ranging from fundamental physics to climate science to biomedical research. Conservation principles form the bedrock of physical understanding, establishing that certain quantities in nature remain constant despite complex transformations and interactions. These conservation laws reveal the universe's fundamental symmetries, providing powerful analytical tools that enable scientists to solve problems across all physics disciplines, from particle interactions to cosmic evolution. The conservation of energy ranks among the most fundamental principles, stating that energy can neither be created nor destroyed, only converted between forms. When a boulder rolls downhill, gravitational potential energy transforms to kinetic energy, which converts to thermal energy as friction slows the boulder. Throughout these transformations, the total energy remains constant, though its manifestation changes dramatically. This principle revolutionized 19th century physics, unifying previously separate phenomena like heat, light, electricity, and mechanical motion into a coherent theoretical framework. Everyday applications of energy conservation appear throughout technology, Hydroelectric dams convert a gravitational potential energy of elevated water into electrical energy. Automobiles transform chemical energy in fuel to kinetic energy through combustion, then to thermal energy during braking. Even food metabolism demonstrates this principle, with chemical energy from nutrients converting to mechanical energy for movement, thermal energy for body temperature maintenance, and stored chemical energy in tissues. Each process conserves total energy while transforming it between usable and less usable forms. The conservation of momentum extends these principles to motion, establishing that an isolated system's total momentum remains constant, regardless of internal interactions. This vector quantity, the product of mass and velocity, transfers between objects during collisions while maintaining its total magnitude and direction. When a cue ball strikes other balls on a pool table, the total momentum before and after impact remains identical, though distributed differently among the balls. Momentum conservation explains rocket propulsion in the vacuum of space, where exhaust gases expelled backward create equal forward momentum in the spacecraft. It explains recoil when firing guns, where the backward momentum of the weapon balances the forward momentum of the bullet. The principle even governs subatomic particle interactions in particle accelerators, where momentum conservation constrains possible reaction products and helps identify new particles. Angular momentum conservation governs rotating systems, keeping spinning objects in motion unless external torque acts upon them. This principle explains why bicycle wheels remain upright while spinning, why ice skaters spin faster when pulling their arms inward, and why planetary orbits remain stable over billions of years. The principle extends to quantum mechanics, where electron orbitals and particle spin follow the same conservation law despite their counterintuitive quantum nature. The conservation of electric charge stands as one of the most precisely verified physical laws. In all observed physical processes, from chemical reactions to nuclear transformations to particle creation and annihilation, the net electric charge remains exactly constant. Even when matter converts entirely to energy in particle-antiparticle annihilation, charged particles produce photons with zero charge only when paired with their oppositely charged counterparts, maintaining precise charge balance. This charge conservation principle underlies everything from battery operation to electronics to understanding lightning. Electrical circuits maintain continuous charge flow rather than accumulating or depleting charge. When electrostatic charges build up on surfaces, they eventually discharge through conductive paths that maintain total charge equality. This absolute conservation demonstrates the fundamental nature of electric charge as an invariant property of matter. Mass conservation served as a cornerstone of chemical understanding for centuries, establishing that reactants and products in chemical reactions maintain identical total mass despite rearranging atoms. This principle enabled quantitative chemistry development and industrial chemical process design. Einstein's relativity later revealed that mass and energy are equivalent through E equals mc squared, showing that mass can convert to energy and vice versa while conserving their combined total. This equivalence manifests most dramatically in nuclear reactions, where small mass differences convert to enormous energy. The Sun converts approximately 4 million tons of mass into energy every second through fusion. Yet this represents a tiny fraction of its total mass, enabling billions of years of energy production. Nuclear power plants similarly convert mass directly to energy through fission processes, demonstrating mass energy conservation on practical scales. The conservation of baryon number governs the behavior of particles including protons and neutrons, establishing that the universe maintains a constant number of baryons minus antibaryons. This principle explains why protons appear extremely stable, with lifetimes exceeding 10 to the power of 34 years in most theoretical models. Any proton decay would violate baryon conservation and has never been experimentally observed, despite extensive searches. This conservation law explains why ordinary matter dominates over antimatter in our observable universe, though the underlying reason for initial baryon asymmetry remains a significant cosmological question. Lepton number conservation similarly governs electron-like particles and their neutrinos. In a particle interactions and decays, the total number of leptons minus antileptons remains constant, though recent discoveries suggest neutrino oscillations may violate strict lepton flavor conservation. These conservation principles provide crucial constraints for particle physics models and help explain why certain theoretical particle transformations remain unobserved despite energetic favorability. The symmetry connection to conservation laws represents one of physics' most profound insights. Emmy Noether's theorem established that each conservation law corresponds to a specific symmetry in physical laws. Energy conservation emerges from time translation symmetry. Physical laws remain identical regardless of when they occur. Momentum conservation corresponds to space translation symmetry. Physics remains consistent regardless of location. Angular momentum conservation stems from rotational symmetry. Physical laws don't prefer any particular orientation. This deep connection between symmetry and conservation provides theoretical foundations for fundamental physics, while guiding research into new conservation principles. When apparent violations occur, they often reveal new physics, as when apparent energy non-conservation in beta decay led to neutrino discovery, preserving the conservation principle once the full picture emerged. Conservation principles provide powerful analytical tools across physics disciplines. In mechanics, engineers analyze complex systems by tracking conserved quantities between initial and final states without detailed path calculations. In particle physics, conservation laws determine which reactions can occur and help identify particles through missing energy or momentum analysis. In astrophysics, conservation principles enable understanding stellar evolution and galactic dynamics despite impossibility of direct experimentation. The predictive power of conservation laws enables scientific advancements even when detailed mechanisms remain unknown. Early thermodynamics developed practical applications before atomic theory was established, using energy conservation to analyze steam engines and industrial processes. Similarly, nuclear physics progressed through applying conservation principles to radioactive decay before detailed understanding of strong and weak nuclear forces emerged. While conservation laws appear absolute within their domains of applicability, defining appropriate system boundaries remains crucial for practical application. Energy appears non-conserved in biological organisms, unless accounting for food intake and waste heat. Momentum seems violated when considering partial systems, but maintains conservation when including reaction forces from supporting surfaces or surrounding media. These practical considerations highlight the importance of proper system definition when applying conservation principles. Conservation laws transcend specific theories, remaining valid across scientific paradigm shifts. While explanatory frameworks evolve, from classical mechanics to quantum theory to potential future models, conservation principles maintain validity, representing nature's fundamental invariance. This persistence across theoretical revolutions demonstrates their deep connection to reality's foundational structure, rather than merely representing human-constructed models or approximations. Waves transport energy through space and matter without permanently displacing the medium itself. This unique characteristic distinguishes waves from other physical phenomena, enabling energy and information transfer across distances without requiring physical objects to travel the entire path. From ocean swells to electromagnetic radiation to quantum probability distributions, waves permeate physical reality across all scales. Wave motion occurs whenever a disturbance propagates through a medium or field. The classic example begins with a stone dropped into still water, creating circular ripples, propagating outward. Each water molecule primarily moves up and down, rather than traveling with the wave, yet the wave pattern itself moves horizontally across the surface, carrying energy from the impact point to distant locations. This distinction between medium movement and wave propagation represents waves' essential characteristic. Waves manifest through several fundamental properties. Wavelength measures the distance between successive wave peaks or troughs, while frequency indicates how many complete cycles pass a fixed point per second. Amplitude describes displacement, magnitude from equilibrium position, directly related to the wave's energy content. Wave speed equals wavelength multiplied by frequency, with the speed determined by the medium's properties, rather than the wave's characteristics in most cases. Two primary wave categories exist based on medium particle movement relative to propagation direction. Transverse waves exhibit particle motion perpendicular to the wave direction, like plucked guitar strings, or electromagnetic radiation, where electric and magnetic fields oscillate perpendicular to travel direction. Longitudinal waves feature particle displacement parallel to propagation direction, like sound waves, where air molecules compress and rarefy along the sound travel path. Some complex waves, such as water waves, combine both transverse and longitudinal components. Wave interactions create distinctive phenomena not observed in particle-based physics. When waves meet, their amplitudes add through superposition. Constructive interference occurs when peaks align with peaks, creating larger amplitudes, while destructive interference happens when peaks align with troughs, potentially canceling completely. This superposition principle explains acoustical beats, noise-canceling headphones, and optical interference patterns used in precision measurements. Diffraction occurs when waves encounter obstacles or openings, causing them to bend around corners or spread after passing through apertures. This behavior explains why you can hear someone around a corner despite not seeing them. Sound waves diffract around obstacles, while light waves generally do not diffract significantly around macroscopic objects due to their much shorter wavelengths. However, light diffraction becomes apparent through narrow slits or small apertures, creating distinctive patterns that reveal light's wave nature. Wave reflection happens when waves encounter boundaries between different media, bouncing back while potentially changing phase. Echoes demonstrate sound wave reflection, while mirrors show light reflection. Partial reflection occurs at boundaries where some energy reflects while some transmits into the new medium, often with direction change, known as refraction. This refraction explains why objects appear displaced when viewed through water and why prisms separate white light into component colors. Different wavelengths refract at different angles. Standing waves form when waves reflect back upon themselves, creating interference patterns with stationary nodes, points of zero amplitude, and antinodes, points of maximum amplitude. Musical instruments utilize standing waves to produce specific tones. Guitar strings, organ pipes, and drum membranes all generate standing wave patterns with frequencies determined by their physical dimensions. Standing waves also appear in quantum mechanics, where electron orbitals represent standing matter waves around atomic nuclei. The Doppler effect creates frequency shifts when wave sources and observers move relative to each other. Approaching sources produce higher observed frequencies, shorter wavelengths, while receding sources create lower frequencies, longer wavelengths. This effect explains why ambulance sirens drop in pitch as they pass by, and provides astronomical measurements through redshift or blue shift of light from moving celestial objects. Radar systems utilize this principle to measure vehicle speeds by detecting frequency changes in reflected radio waves. Electromagnetic waves represent a crucial wave category that requires no material medium, propagating through vacuum at light speed, approximately 3 × 10 to the power of 8 meters per second. These waves consist of oscillating electric and magnetic fields perpendicular to each other and to the propagation direction. The electromagnetic spectrum encompasses radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays, all identical in nature but differing in wavelength and frequency, which determines their interactions with matter. Mechanical waves require material media for propagation. Sound waves travel through solids, liquids, or gases as pressure variations, with speed depending on medium elasticity and density. Sound travels faster through solids, about 5,000 meters per second in steel, than liquids, about 1,500 meters per second in water, or gases, about 343 meters per second in air at room temperature. Seismic waves generated by earthquakes include primary P waves, longitudinal, and secondary S waves, transverse, with P waves traveling faster and moving through all materials, while S waves cannot propagate through liquids, providing valuable information about Earth's internal structure. Wave packets represent localized wave groups with finite spatial extent, combining multiple wave components with slightly different wavelengths and frequencies. This combination creates localized disturbances that maintain their shape while propagating, though dispersion, wavelength-dependent speed variation, can cause wave packets to spread over time. Wave packets bridge classical waves and quantum particles through wave-particle duality, where matter and energy exhibit both wave and particle properties depending on measurement context. Quantum mechanics fundamentally incorporates wave concepts through wave functions that describe probability distributions for particle positions and other properties. Schrödinger's wave equation governs these wave functions, with solutions revealing quantized energy states in atoms and molecules. These matter waves explain electron diffraction patterns and the stability of atomic orbitals, demonstrating that wave behavior extends beyond classical contexts into the quantum realm, where particles themselves exhibit wave-like properties. Modern technologies extensively utilize wave principles. Telecommunications transmit information through electromagnetic wave modulation. Medical ultrasound imaging uses high-frequency sound wave reflection to visualize internal structures. Optical fibers guide light waves through total internal reflection for data transmission. Radar and LiDAR measure distances and velocities through an electromagnetic wave reflection timing. Noise-canceling technology employs destructive interference to eliminate unwanted sound. These diverse applications demonstrate waves' practical importance beyond theoretical interest. Wave energy harvesting represents an emerging technology field. Ocean wave energy converters capture kinetic energy from surface waves for electricity generation. Piezoelectric materials convert mechanical wave energy from vibrations into electrical energy for small-scale applications. Acoustic metamaterials manipulate sound waves for improved energy harvesting or noise control. These approaches potentially enable energy capture from previously unused ambient sources. Wave phenomena unify seemingly disparate fields through common mathematical descriptions. Oscillations in electrical circuits, mechanical systems, and quantum fields all follow similar wave equations despite their different physical contexts. This mathematical commonality enables knowledge transfer between fields and suggests deeper connections within physical reality. The universality of wave mathematics provides powerful analytical tools applicable across scientific and engineering disciplines. Understanding wave behavior revolutionized modern physics through quantum mechanics and relativity. Einstein's work on the photoelectric effect established light's particle nature while maintaining its wave characteristics. De Broglie's matter-wave hypothesis extended wave-particle duality to all matter. Quantum field theory ultimately unified these perspectives by describing fundamental particles as excitations in underlying quantum fields that propagate as waves. These developments fundamentally transformed our understanding of reality's building blocks. Sound represents mechanical wave propagation through material media, transferring energy via pressure variations without permanent particle displacement. This everyday phenomenon surrounds us constantly, from speech communication to music appreciation to environmental awareness, while simultaneously serving as a crucial investigative tool across scientific and medical fields. At its physical foundation, sound consists of longitudinal pressure waves, alternating compressions and rarefactions propagating through gases, liquids, or solids. Air molecules briefly push closer together in compression regions, then spread further apart in rarefaction regions, creating pressure variations detected by our ears or measurement instruments. Unlike electromagnetic waves that can travel through vacuum, sound requires a material medium for transmission, explaining why space remains silent despite violent cosmic events. Sound speed varies dramatically between materials depending on molecular structure and bonding. It travels approximately 343 meters per second, 1,125 feet per second, through air at room temperature, 1,481 meters per second through water, and 5,120 meters per second through steel. This variation explains why underwater sounds reach swimmers from all directions with minimal directional cues. and why placing your ear against a rail lets you hear approaching trains long before airborne sound arrives. Temperature also affects sound speed. Warmer air transmits sound faster, creating interesting atmospheric effects when temperature gradients bend sound waves. The perception of sound involves several properties. Pitch corresponds to frequency, how many pressure oscillations occur per second, measured in hertz. Humans typically hear frequencies between 20 hertz and 20,000 hertz, with this range narrowing with age, particularly at higher frequencies. Loudness relates to amplitude, the pressure variation magnitude measured logarithmically in decibels, dB. This logarithmic scale explains why 60 decibels sounds twice as loud as 50 decibels, not merely 20% louder. Timbre distinguishes sounds with identical pitch and loudness based on harmonic content and envelope characteristics, allowing us to differentiate instruments or voices playing the same note. Sound propagation demonstrates wave behaviors including reflection, refraction, diffraction, and interference. Reflection creates echoes when sound bounces off surfaces, with reflection characteristics dependent on material properties. Hard surfaces reflect most energy, while soft materials absorb sound. Refraction occurs when sound passes between media with different propagation speeds or through media with varying properties, causing sound to bend. This explains why voices carry further over water at night when temperature inversions bend sound waves downward instead of allowing them to dissipate upward. Diffraction allows sound to bend around obstacles or spread after passing through openings. This property explains why you can hear someone speaking around a corner despite not seeing them. Sound waves diffract around the corner, while light waves generally do not diffract significantly around macroscopic objects, though light diffraction becomes apparent through small apertures. Interference creates reinforcement or cancellation when sound waves combine, producing acoustic dead spots in concert halls or resonant amplification at specific frequencies. The Doppler effect shifts frequency when sources or listeners move relative to each other. Approaching sound sources produce higher observed frequencies, while receding sources create lower frequencies, explaining why train whistles or sirens drop in pitch as they pass by. This effect enables radar measurement of vehicle speeds and provides crucial astronomical data through redshift measurements of distant galaxies. Resonance occurs when objects vibrate at their natural frequencies in response to sound waves, potentially creating dramatic amplification. Musical instruments utilize resonance to amplify specific frequencies. String instruments through hollow bodies, wind instruments through air columns, percussion through membrane or material properties. Resonance can also create dramatic engineering failures, as with the infamous Tacoma Narrows Bridge collapse when wind-induced vibrations matched the structure's resonant frequency. The study of acoustics, sound's scientific application, spans numerous fields. Architectural acoustics design spaces with appropriate sound reflection, absorption, and diffusion properties for intended purposes, from concert halls optimized for musical clarity to restaurants engineered to remain conversational despite high occupancy. Environmental acoustics addresses noise pollution, impacts on wildlife, and human health. Ultrasonic imaging utilizes sound frequencies beyond human hearing, greater than 20 kilohertz, for medical diagnostics and industrial inspection. Underwater acoustics enables sonar navigation, and oceanographic research through sound transmission characteristics in aquatic environments. Sound's fundamental role in communication shapes human evolution and culture. Human speech uses precisely controlled air pressure modulation to create complex sound patterns representing language. Music across cultures utilizes organized sound to convey emotion and meaning through rhythmic, melodic, and harmonic structures. Natural soundscapes provide crucial environmental information, approaching weather, potential dangers, available resources, and social cues from other species. These diverse roles highlight sound's centrality to human experience beyond mere physical phenomenon. The human auditory system demonstrates remarkable sensitivity and processing capability. The outer ear, pinna, collects and focuses sound waves toward the ear canal, where they vibrate the eardrum. 3 tiny bones, ossicles, in the middle ear efficiently transfer these vibrations to the fluid-filled cochlea, where specialized hair cells convert mechanical vibrations to neural signals. This process detects pressure variations as small as 20 micropascals, billions of times smaller than atmospheric pressure, while simultaneously handling sounds millions of times more intense without damage through protective mechanisms. The brain processes these signals to extract meaning, locate sources, filter background noise, and interpret emotional content, demonstrating sophisticated neural processing that even advanced artificial systems struggle to replicate. Beyond human perception, animals utilize sound across extraordinary frequency ranges. Elephants communicate through infrasound, less than 20 hertz, that travels many kilometers through ground and air. Bats and dolphins navigate through echolocation, emitting ultrasonic pulses and analyzing echoed returns to create detailed environmental maps. Certain moth species detect bat echolocation and execute evasive maneuvers, while some tigers produce infrasonic growls that paralyze prey through frequency-specific responses. These diverse adaptations demonstrate sound's evolutionary importance across species. Musical acoustics reveals fascinating relationships between mathematics and perception. The octave, where frequency doubles, creates perceived pitch similarity across cultures. Harmonic relationships based on whole number frequency ratios, 2 to 1 octaves, 3 to 2 perfect fifths, 4 to 1, 3 perfect fourths, form the foundation for musical scales across diverse traditions. These mathematical relationships create consonance and dissonance patterns that composers manipulate for emotional effect. Even timbre, the distinctive sound quality of instruments, results from specific harmonic series patterns, unique to each sound source. Technological applications utilize sound principles across diverse fields. Ultrasonic cleaners remove contaminants from delicate items through high-frequency cavitation. Sonar systems map ocean floors and locate subsurface objects. Acoustic levitation suspends small objects using precisely controlled standing waves. Medical ultrasound provides non-invasive diagnostic imaging. Noise-canceling headphones generate inverse sound waves to create destructive interference with ambient noise. These applications demonstrate sound's practical utility beyond communication and artistic expression. Sound also reveals information about material properties. Tapping objects produces characteristic sounds depending on material composition, density, and structure. Medical professionals use percussion and auscultation to assess internal organ conditions. Industrial quality control utilizes acoustic testing to identify defects in manufactured components. Seismologists analyze seismic wave propagation, essentially very low-frequency sound through Earth structure, to understand planetary composition. These diagnostic applications demonstrate sound's value as an investigative tool across disciplines. The physics of sound bridges classical and quantum understanding, while macroscopic sound waves follow classical wave equations. Their underlying energy arrives in quantized packets called phonons, quantized vibrational energy similar to photons for electromagnetic radiation. This quantum perspective becomes increasingly important when analyzing thermal properties of materials, where phonons carry thermal energy, or in advanced acoustic metamaterials designed with properties not found in natural materials. Sound represents perhaps the most immediately perceptible example of wave physics in everyday experience, making it both practically important and conceptually valuable for understanding broader wave phenomena across physics disciplines. Light constitutes electromagnetic radiation visible to the human eye, occupying a narrow band of the electromagnetic spectrum between ultraviolet and infrared wavelengths. This remarkable phenomenon enables vision, drives photosynthesis, and forms the foundation for countless technologies while simultaneously revealing fundamental insights about the universe's structure and behavior. Light exhibits dual nature, functioning both as waves and particles. As waves, light consists of oscillating electric and magnetic fields perpendicular to each other and to the propagation direction. These waves travel at approximately 3 × 10 to the power of 8 meters per second in vacuum, the universal speed limit discovered by Einstein. As particles, light comprises photons, discrete energy packets with energy proportional to frequency through Planck's constant. This wave-particle duality, first suggested for light and later extended to all matter, revolutionized physics and helped birth quantum mechanics. The visible spectrum spans wavelengths from approximately 380 nanometers, violet, to 740 nanometers, red, with each wavelength perceived as different colors. White light contains all visible wavelengths, while objects appear colored by selectively absorbing certain wavelengths and reflecting or transmitting others. A red apple absorbs most wavelengths except red, which reflects to our eyes. Transparent materials like glass transmit most visible wavelengths with minimal absorption, while translucent materials scatter light during transmission, and opaque materials absorb or reflect without transmission. Light interacts with matter through several mechanisms. Reflection occurs when light bounces off surfaces, following the principle that incidence angle equals reflection angle. Refraction happens when light passes between media with different propagation speeds, causing direction change, according to Snell's law. This principle explains why objects appear displaced when viewed through water and enables optical instruments like lenses. Diffraction occurs when light encounters obstacles or apertures comparable to its wavelength, causing it to spread and bend around edges, producing interference patterns that confirm light's wave nature. Optical phenomena abound in nature. Rainbows form when sunlight refracts through raindrops, separating into component colors through dispersion, where different wavelengths refract at slightly different angles. Mirages appear when light refracts through air layers with varying temperatures, creating inverted images of distant objects. The sky appears blue because air molecules scatter shorter blue wavelengths more effectively than longer wavelengths through Rayleigh scattering. Sunset reds result from sunlight traveling through more atmosphere, leaving primarily longer wavelengths after shorter wavelengths scatter away. The electromagnetic spectrum extends far beyond visible light. Radio waves, wavelengths from millimeters to kilometers, enable telecommunications. Microwaves, millimeters to centimeters, cook food by exciting water molecules and power radar systems. Infrared radiation, 740 nanometers to 1 millimeter, transfers heat and enables night vision. Ultraviolet light, 10 nanometers to 380 nanometers, causes sunburn and reveals details invisible to human eyes. X-rays penetrate soft tissues while being absorbed by denser materials, enabling medical imaging. Gamma rays, the highest energy electromagnetic radiation, sterilize medical equipment and provide insights into nuclear processes and cosmic events. Light's finite speed, though enormous at 300,000 kilometers per second, creates observable consequences. Looking at distant cosmic objects means seeing them as they appeared in the past. The Andromeda Galaxy appears as it was 2.5 million years ago. This light time delay affects everything from astronomical observations to high-frequency trading, where microsecond transmission advantages create meaningful financial opportunities. Even video conferencing experiences noticeable delays when signals travel intercontinental distances. Einstein's special relativity emerged from analyzing light's properties, particularly the constancy of light speed for all observers, regardless of relative motion. This counterintuitive principle leads to time dilation, length contraction, and mass energy equivalence, E equals mc squared, fundamentally changing our understanding of space and time. General relativity extended these insights, showing that gravity curves space-time, causing light to follow curved paths near massive objects, a prediction dramatically confirmed during a 1919 solar eclipse. The technological applications of light pervade modern civilization. Fiber optic communications transmit information through total internal reflection of laser light within glass fibers, enabling global internet infrastructure. Digital cameras convert light to electronic signals through photoelectric effects in semiconductor sensors. Lasers produce coherent, monochromatic light through stimulated emission, finding applications from surgical tools to barcode scanners to industrial cutting. Photovoltaic cells convert light directly to electricity, powering satellites, and increasingly supplying renewable energy to power grids. Human vision represents a remarkable system evolved to detect and process light. The eye focuses light through the cornea and lens onto the retina, where specialized photoreceptor cells convert light to neural signals. Rods provide high-sensitivity monochromatic vision in low light, while cones enable color vision in 3 primary bands, roughly corresponding to red, green, and blue wavelengths. The brain processes these signals to construct visual perceptions, extracting information about object boundaries, colors, movements, and spatial relationships that guide our interaction with the environment. Light measurement employs various units for different aspects. Luminous intensity, measured in candelas, quantifies light emission in particular directions. Luminous flux, lumens, measures total light output from sources. Illuminance, lux, measures light incident on surfaces. These photometric units account for human visual sensitivity across wavelengths. differing from radiometric units that measure absolute electromagnetic power regardless of visual perception. The photon model, established by Einstein, explains phenomena classical wave theory couldn't address. The photoelectric effect, where light striking certain materials ejects electrons, occurs only above threshold frequencies regardless of intensity, contradicting wave predictions but perfectly matching photon theory. Similarly, black body radiation spectra and atomic emission lines required quantum explanations involving discrete energy transfers through photons, helping establish quantum mechanics foundation. Light's polarization, the orientation of its electric field oscillations, reveals additional properties invisible to human perception. Many animals, including bees and certain fish, see polarized light patterns used for navigation. Polarizing filters selectively transmit specific orientations, enabling glare reduction in sunglasses and photographic filters. LCD screens regulate light transmission through controlled polarization, while optical activity, polarization rotation by certain molecules, enables sugar concentration measurement in manufacturing and medicine. Light's study has revolutionized our understanding of the universe's fundamental nature, while simultaneously enabling technologies that transform human experience, truly bridging the theoretical and practical domains of physics. Electricity represents the flow and behavior of electric charge, a fundamental force driving countless natural phenomena and technological applications. This physical property manifests through charged particles, primarily electrons in practical applications, that create electric fields, generate magnetic effects when moving, and transfer energy through conductors and circuits. At its foundation, electricity arises from electric charge, a fundamental property of matter coming in positive and negative varieties. Electrons carry negative charge, while protons carry positive charge, with like charges repelling and opposite charges attracting. This electrostatic force follows an inverse square relationship, diminishing with distance squared, while extending theoretically to infinity. Electric current measures charge flow rate through conductors, measured in amperes. 1 ampere equals 1 coulomb of charge flowing per second. Conductors, like metals, contain loosely bound electrons that move relatively freely, while insulators tightly bind electrons, preventing significant flow. Semiconductors occupy the middle ground, with properties manipulable through doping, deliberately introducing impurities to control conductivity. Potential difference, measured in volts, represents the electric potential energy difference between points in an electric field. This voltage drives current flow. Higher voltage creating stronger electrical pressure that pushes electrons through conductors. The relationship between voltage, current, and resistance forms Ohm's law, V equals IR, where voltage equals current multiplied by resistance. This fundamental principle enables predicting circuit behavior across countless applications. Electric power, the rate of energy transfer through electrical means, equals voltage multiplied by current, P equals VI, measured in watts. This relationship explains why high-voltage transmission lines efficiently transport electricity over long distances, maintaining high voltage while reducing current for the same power delivery reduces energy losses from wire resistance. Resistance, measured in ohms, quantifies how materials oppose current flow, converting electrical energy to thermal energy. This property depends on material composition, temperature, length, and cross-sectional area. Resistors deliberately introduce specific resistance values into circuits to control current flow or divide voltage. Superconductors represent the opposite extreme, materials exhibiting zero electrical resistance below critical temperatures, enabling lossless current flow with applications in powerful electromagnets and sensitive detectors. Electrical circuit components manipulate charge flow for specific purposes. Capacitors store charge separation, accumulating opposite charges on conductive plates separated by insulators. Inductors store energy in magnetic fields created by current flow, resisting current changes. Transformers transfer energy between circuits through electromagnetic induction, enabling voltage conversion, crucial for power distribution. Diodes allow current flow in only one direction, while transistors control current flow through small input signals, forming the foundation for digital electronics. Circuit configurations come in two primary arrangements. Series circuits provide a single path for current, with identical current through all components, but voltage divided among them. Parallel circuits offer multiple paths, maintaining identical voltage across components while dividing current between paths. Complex circuits combine these arrangements to achieve sophisticated functionality from simple components. Electromagnetic induction, discovered by Michael Faraday, reveals the profound connection between electricity and magnetism. Changing magnetic fields induce electric currents in conductors, while moving charges create magnetic fields. This reciprocal relationship enables electric generators that convert mechanical energy to electrical energy by moving conductors through magnetic fields, and electric motors that convert electrical energy back to mechanical motion. Technologies that transformed human civilization. Digital electronics revolutionized technology by representing information through discrete electrical states rather than continuous values. Binary logic uses voltage levels to represent ones and zeros, with transistors functioning as switches to control these states. Integrated circuits combine millions or billions of transistors on silicon wafers, creating microprocessors that perform complex calculations through logical operations on these binary values. This digital foundation enables computers, smartphones, and countless other devices transforming modern life. Electricity generation occurs through various methods. Thermal power plants burn fossil fuels or use nuclear reactions to heat water, creating steam that drives turbines connected to generators. Hydroelectric facilities convert water's gravitational potential energy to electricity. Wind turbines harness atmospheric flows, while solar panels directly convert light to electricity through the photovoltaic effect. Each method presents different economic, environmental, and reliability characteristics influencing energy infrastructure development. Electric power distribution forms a sophisticated network transmitting electricity from generation facilities to end users. High-voltage transmission lines minimize energy losses over long distances, with transformers stepping voltage down progressively toward consumer levels. This grid must constantly balance generation with consumption, as electricity presents unique challenges regarding large-scale storage. Smart grid technologies increasingly incorporate sensors, communication systems, and automated controls to improve reliability and efficiency. Electrical safety concerns arise from current flowing through human bodies, potentially disrupting cardiac rhythm or causing thermal burns. Grounding systems direct fault currents safely to Earth, while circuit breakers and fuses interrupt excessive currents before damage occurs. Insulation prevents contact with energized conductors, while residual current devices detect imbalances indicating potential human contact. These layered protection systems make electricity relatively safe despite its inherent hazards. Bioelectricity plays essential roles in living organisms. Nerve cells transmit signals through electrical impulses, with sodium and potassium ion movements creating action potentials that propagate along neurons. The heart's specialized conduction system coordinates electrical impulses, controlling cardiac muscle contractions. Brain activity generates measurable electrical patterns recorded through electroencephalography, EEG, while muscle activation produces signals detectable via electromyography, EMG. These biological electrical systems demonstrate remarkable sensitivity, specificity, and efficiency. Electrostatic phenomena occur when charge imbalances develop through friction or separation. Static electricity accumulation causes materials to attract or repel each other and can produce dramatic discharges when sufficient voltage develops. Lightning represents nature's most spectacular electrostatic discharge, equalizing charge differences between clouds and ground through plasma channels carrying enormous currents. Industrial applications of electrostatics include photocopiers, paint sprayers, and particle filtration systems. Electricity's theoretical understanding evolved dramatically through history. Ancient civilizations observed static electricity and lightning without explanation. The 18th century saw systematic investigation with Coulomb, quantifying electrostatic force, and Volta, developing the first battery. The 19th century brought revolutionary connections between electricity and magnetism through work by Ampere, Faraday, and Maxwell, culminating in Maxwell's equations, unifying electric and magnetic fields into a coherent electromagnetic theory. This theoretical foundation, combined with practical engineering developments, transformed electricity from mysterious phenomenon to ubiquitous power source driving modern civilization. Magnetism represents one of nature's fundamental forces, arising from moving electric charges and intrinsic magnetic moments of elementary particles. This phenomenon creates invisible fields that exert forces on other magnetic materials and moving charges, enabling technologies from simple compasses to sophisticated medical imaging systems. Magnetic fields originate from two primary sources: electric currents and magnetic materials. Moving electric charges, whether flowing through wires or orbiting within atoms, generate magnetic fields circling the current path. Certain materials like iron, nickel, and cobalt contain electrons with aligned intrinsic magnetic moments that collectively produce macroscopic magnetic fields. These ferromagnetic materials form permanent magnets that maintain their magnetic properties without external power. The relationship between electricity and magnetism, discovered in the 19th century, revealed that changing magnetic fields induce electric currents in conductors, while moving charges generate magnetic fields. This electromagnetic relationship enables generators to convert mechanical energy to electrical energy by moving conductors through magnetic fields, and motors to convert electrical energy back to mechanical motion, technologies that revolutionized civilization. Magnetic field strength diminishes with distance, typically following inverse cube relationships rather than the inverse square pattern of gravitational and electrostatic forces. This more rapid fall-off creates strongly localized effects that enable precise control in applications ranging from computer hard drives to particle accelerators. Earth itself generates a substantial magnetic field through complex geodynamo processes in its liquid outer core, where convection currents in the electrically conductive iron-nickel material create a self-sustaining magnetic field. This geomagnetic field shields the planet from solar radiation while enabling navigation through compass alignment and creating spectacular aurora displays when solar particles interact with the upper atmosphere along magnetic field lines. Quantum mechanics describes nature's behavior at the smallest scales, where classical physics fails to explain observed phenomena. This revolutionary framework emerged in the early 20th century, when experiments revealed particles sometimes behaving like waves and energy coming in discrete packets rather than continuous flows. The core principles of quantum mechanics include wave-particle duality, quantization, uncertainty, and probability. Wave-particle duality means objects exhibit both particle-like and wave-like properties depending on how they're observed. Quantization indicates certain physical properties only take discrete values rather than continuous ranges. Heisenberg's uncertainty principle states we cannot simultaneously know a particle's exact position and momentum with perfect precision. Probability replaces determinism, with quantum states described by wave functions representing probability distributions rather than definite values. Schrödinger's equation governs how these quantum wave functions evolve over time, similar to how Newton's laws govern classical objects. Solutions to this equation reveal quantized energy levels in atoms, explaining atomic spectra and chemical bonding patterns. Quantum tunneling allows particles to penetrate energy barriers impossible in classical physics, enabling nuclear fusion in stars and quantum computing applications. Quantum entanglement creates perhaps the most counterintuitive quantum phenomenon: particles becoming correlated, such that measuring one instantly determines properties of another, regardless of separation distance. Einstein described this as spooky action at a distance, though experiments consistently confirm this behavior without allowing faster-than-light communication. These quantum principles underpin technologies including lasers, transistors, MRI machines, and emerging quantum computers, demonstrating how this abstract theoretical framework translates into practical applications that transform modern life. Relativity fundamentally changed our understanding of space, time, and gravity through two theories developed by Albert Einstein. Special relativity, 1905, established that the speed of light remains constant for all observers, regardless of relative motion, leading to several counterintuitive consequences. Time dilation causes moving clocks to tick slower relative to stationary observers. Length contraction shortens objects in their direction of motion. Mass increases with velocity, approaching infinity as speed approaches light speed, explaining why matter cannot reach light speed. The famous equation E equals mc squared emerged from this theory, showing mass and energy equivalence. General relativity, 1915, expanded these concepts to include gravity, reimagining it not as a force but as space-time curvature caused by mass and energy. Massive objects like stars and planets curve the fabric of space-time, with other objects following these curves rather than experiencing a direct pulling force. This explains orbital motions and predicts phenomena like gravitational waves, gravitational lensing, and black holes. The theory accurately predicted Mercury's orbital precession and light bending around the Sun, confirmed during a 1919 solar eclipse. More recent confirmations include gravitational waves detected in 2015 and the first black hole image captured in 2019. Relativity affects everyday technologies despite its seemingly abstract nature. GPS satellites must account for both special and general relativistic effects, as their high speed and distance from Earth's gravitational field cause their clocks to run faster than surface clocks by about 38 microseconds daily, enough to create navigational errors of kilometers if uncorrected. These theories fundamentally connected space and time into a unified space-time continuum, revolutionizing physics and showing that our intuitive understanding of reality breaks down at extreme speeds and gravitational conditions. Cosmology studies the universe's origin, evolution, structure, and ultimate fate. This scientific field combines observational astronomy with theoretical physics to understand reality at its largest scales and earliest moments. The Big Bang theory forms modern cosmology's cornerstone, proposing the universe began approximately 13.8 billion years ago from an extremely hot, dense state that has expanded continuously since. Evidence supporting this model includes cosmic microwave background radiation, the afterglow of the early universe, light element abundances created during primordial nucleosynthesis, and the observed galaxy recession, indicating expanding space. Cosmic inflation theory suggests the universe underwent exponential expansion during its first fraction of a second, explaining the observed uniformity at large scales, while allowing density fluctuations that seeded cosmic structure. These tiny quantum fluctuations, stretched by inflation, became the foundation for galaxy formation as gravity gradually amplified these density variations. Dark matter and dark energy represent major cosmological mysteries. Dark matter, detected only through gravitational effects, appears to comprise about 27% of the universe, providing the gravitational scaffolding for galaxy formation. Dark energy, comprising roughly 68% of the universe's content, drives accelerating cosmic expansion discovered in the 1990s through observations of distant supernovae. The cosmic web describes the universe's large-scale structure, where galaxies form clusters and filaments surrounding vast voids. This pattern emerged from initial density fluctuations under gravity's influence over billions of years. Cosmological models suggest several possible fates for the universe, including endless expansion into a cold, diffuse state, the Big Freeze, a potential reversal of expansion into contraction, the Big Crunch, or other scenarios depending on dark energy's nature and cosmic density parameters. Applied physics transforms theoretical understanding into practical technologies that reshape human civilization. While pure physics seeks to understand nature's fundamental principles, applied physics leverages this knowledge to create solutions for real-world challenges across diverse domains. Materials science represents a primary applied physics field, studying how atomic and molecular structures determine material properties. This discipline enables development of semiconductors powering electronic devices, superconductors for efficient power transmission, advanced ceramics for extreme environments, and nanomaterials with unique properties at molecular scales. Medical physics applies physical principles to healthcare through technologies like MRI machines using nuclear magnetic resonance to visualize soft tissues, radiation therapy precisely targeting cancer cells, ultrasound imaging using sound wave reflection, and laser surgery employing focused light energy. These applications demonstrate how abstract concepts like quantum mechanics and wave phenomena translate into life-saving technologies. Renewable energy technologies apply thermodynamics, electromagnetics, and quantum physics to address energy challenges. Photovoltaic cells convert sunlight directly to electricity through semiconductor physics. Wind turbines apply fluid dynamics and electromagnetic induction principles. Batteries store energy through electrochemical reactions governed by electron transfer physics. These technologies collectively address climate concerns while meeting growing energy demands. Communication systems depend on electromagnetic wave properties for everything from cellular networks to satellite communications to fiber optic internet infrastructure. Understanding wave propagation, modulation techniques, and signal processing enables the information age's connectivity. Measuring instruments ranging from atomic clocks to gravitational wave detectors to electron microscopes demonstrate how theoretical understanding enables increasingly precise observation of natural phenomena, creating a virtuous cycle where better measurements lead to refined theories that enable still more advanced instruments. Applied physics represents the bridge between understanding the universe and harnessing its principles to improve human life, demonstrating the profound practical value of pursuing fundamental knowledge. Up next, you've got two more standout theory right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out.